Hey, Asher.
Hey, can you hear me all right?
Yeah, one second. Okay, cool. Okay. I don't need that unmuted. Before you start, Asher, I'll give a quick intro. Hey everybody, welcome to the last day. I saw a few of you made a mad dash to the bus. Glad you all were able to make it. So let's go ahead and get started. So again, today, day 5, final day. Thanks everyone for hanging in there and staying with us this whole time. We're going to start off with a Komodo presentation tutorial from Asher Pembroke, who is online now to present virtually. Then a little bit later, we'll hear from Alexandre Schultz, who's in the back, about Speasy. Russell will be talking about OMMBV. And then we'll have a bit of a Python learning session split between Russell Stoneback and John Mehoff, who was with SpacePy. And then we will wrap up for the whole summer school. You've seen this all a million times before at this point, but again, direct all the questions for each project to the right channel, all tech questions to tech questions and so forth, and you have your cards. I presented this yesterday. I won't present it again today, but it'll be in the wrap-up slides and we'll be sending those out so you'll have the instructions for everything there. So again, always check general for links. Keep using our hashtags if you want on social media. When we close those back doors, use that opening instead to go to the bathroom. And just a couple PSAs. We shortened the coffee break today. It'll be 20 minutes instead of 45 minutes so that we can leave earlier. And then there were some NASA and PySet stickers handed out, and there may also be Senpai stickers still. If you didn't get one, Russell has the PySat ones and Jeff has the NASA ones. So go get your thing. And that's all I have. So Asher, you're up.
Great, thank you. So I'm switching over to, can everyone see my screen?
Yeah, can you just zoom in a little bit, maybe, just to be sure?
Maximize. How do I hide the sidebar?
Anyone remember the keyboard shortcut for that?
Oh, there we go.
Figured it out. Cool.
Yes, it was so the interface was so intuitive. I just happened naturally. Yeah, so here's we already talked about Komodo, and it's kind of fitting that this is on the last day because you already have experience with many of the PyHC packages, which Komodo is meant to sit on top of. I should say that before we begin, that if you follow along in the tutorial from your machine at home or there in the classroom, you may see a couple bugs related to the differences between the latest version of Komodo and the one that's installed in Helio Cloud. We made some, I wouldn't say last minute, but some some changes that were meant to make things easier, but they did also break things, as is common with bleeding edge technology. So there's a couple commands if you want to follow along directly that you would run in the notebook. So these two commands, so pip install Komodo upgrade, that will grab the latest version of Komodo. I've already done it here. And then the pip uninstall numerical expressions. It's okay if you don't do that. Just let me know maybe in the chat if you see weirdness otherwise. So yeah, I'd like to also thank Laura Hayes for her insight in when we built the Senpai part, which is going to come at the end of the session. But first I should explain, what is Komodo? We've taken to calling it a functional API for scientific resources. And it took us a few years to come up with this definition, because for a while it was sort of like, what are we doing here exactly? But essentially, Komodo takes, in this image, it kind of summarizes what it's trying to do. It converts original data into functions for use in analysis, visualization, and production. And by production, we mean space weather desks or commercial enterprises, or basically the application layer. So original data can be in any format, because Komodo doesn't actually know what the underlying formats that it uses are. It's a much higher level kind of interface. Sorry about this noise in the background. And we do this conversion through the use of interpolators, which I'll get to in a couple steps and a couple lessons. And then this is basically the high-level user interface that most of us will experience. So let me just see in the chat. I hope it's not too loud in here. All right, moving on. So what is a scientific resource? We said that Komodo is an API for those things. Well, I mean, there's a lot of definitions for what a resource is, but this is one that is useful for us. A source of information or expertise. And I think I should emphasize the expertise side of this. So this is sort of the difference between, so the original data, if you think about like a lawyer has expertise in the field of law. Now you could go and consult all the law books yourself and represent yourself, but it's often not a recommended approach. Or you can consult an expert. And the whole point of the expert is that they understand the underlying information that needs to be exposed to the end user, in this case, their client. And it's their job to summarize that and make it useful or actionable. So scientific resources, we sort of we can think of those in terms of observables on a well-defined domain of scientific interest. They can be purely functional, such as the coordinate systems or just off-the-shelf expressions. And they are often associated with units of measure. So for example, kilograms per meter cubed. And then finally, they're intended for downstream users. So what they are not are the tools themselves. And this is kind of a subtle point, but basically, we're not talking about specific file formats like HDF, CDF, or NetCDF. When in this context, we're not speaking of that. We don't mean specific APIs, and we don't mean specific raw model output or observational data. So those are sort of like, all of these things are basically like, it's like the law books. There are things that are definitely important underlying structures, but they are not a resource in the sense that the average Joe can just pick it off the shelf and understand what's going on. So okay, and what are functions? Well, in math speak, a function maps from a set X to a set Y, assigns to each element. It's this kind of complex idea, or simple, but if you've ever taken high school math, but basically, we can think of pairings of information. So like you have one domain and you assign a single value to each element of that domain. But more colloquially, we would say that functions take inputs and they return outputs. And that's kind of more how computer scientists would think of like what a function is doing, that they represent mappings. But again, just like scientific resources, functions are not the tools themselves. They're not, they're often expressed in a certain way. Like, for example, the right-hand side expression for this function can have that representation. They may be represented by code blocks. So this is the implementation of the function above in Python as a Lambda function. And they may represent variables, but the variables themselves are in this case, they would be the coded domain. They're not the same as the function of like, so row is a common variable used in space weather to represent density. So oftentimes you'll see like a variable just as a blob of data. And that's not what we mean by functions. We mean like, what is that variable in the context of a certain set of positions or times, for example. All right, so why are we harping on functions so much? Why are they so important? The main reason is that functions represent the physical state of the systems that we as physicists are most, obsessed with investigating. So, for example, fields, electromagnetic fields or fluid fields, basically, if you study physics, everything is a field in some sense. And so, we spend quite a bit of time thinking and using these things. There are also derived variables. So in this case, like ram pressure is given by this expression, rho v squared. So here we're seeing, these two things may exist in some raw form, but the end user just wants to visualize or compute this variable. So that's what we call derived variables. Coordinate transformations are a more obvious representation of functions, but a somewhat less obvious one would be something like images. For example, you could think of pixel coordinates as a domain, and then the codomain would be the RGB value or the number of counts for a given pixel.
Yeah, sure.
Go ahead.
Could you just zoom in another like 1 or 2 clicks? Yeah, another. Okay, cool. Thank you.
Okay. Is it too loud in here? Should I try to move outside, or is this are you good? I'm not seeing the chat right now. So
You're good.
Okay, I can probably keep an eye on the chat, but I just tell me if I should pause.
Okay.
All right. And then finally, like solutions to differential equations are generally functions. Like you can't solve a differential equation without a function popping out the other end. And by that, I don't mean a closed form solution. I just mean like anything that can be evaluated to tell you what the result of the differential equation was. Like that's generally there's a way of representing that as a function. So functions are incredibly useful in like understanding physics, and sadly, like they're kind of we sort of have all this machinery in math to deal with functions, but it's often like kind of left by the wayside once we get into discretizing things and plotting things, and this is kind of where Komodo fits in. It's trying to get back to this this functional form of understanding. So one useful thing, there are many useful things you can do with functions that are difficult to do with just raw output or file formats. For example, evaluation. You can evaluate a function at any position in its like domain. You're not just stuck with like the grid that your model output was put on. With some caveats, of course. Like it matters how you evaluate things. It matters like how you do that. The details matter. But conceptually, it exposes evaluations as much more than just the original raw data. Composition is important. This is like how you're able to move from one domain to another domain, for example, in coordinate transformations, but also how you generate pipelines. So we'll talk about function composition later. And then graphing. So like actually visualizing the raw data or the underlying data becomes a lot more straightforward when you already have everything in functions. Okay, so we talked about functions, and then finally, what is an API? Here's a complex definition, but basically think of it as the thing that hides the internal details of how a system works. exposing only the parts a programmer will find useful. In this case, our scientific end user. So kind of the goal of these things, these APIs, is to just hide, like I said, the details. That there are things you need to know when you're designing a library, but there are things that you don't need to know when you're an end user. And we're trying to take that we're trying to take this kind of low coding approach to what our API is trying to do. But that's what we mean by API. And they essentially help us communicate with data living elsewhere. So whether it's in databases or individual file formats or in individual libraries, an API can sort of abstract away the most, well, not the most useful, but the elements of an underlying data source, or that the end user wants to, or that they want to expose to the end user. There's a lot of, and in this case, in that sense, APIs require a lot of design decisions. Like, you're essentially choosing what part of the library or file or database you're going to show to the end user. It's not a replacement for any of those things. It is basically a way to contextualize things that you think the user needs to know. Just as, like, the lawyer is not a replacement for law, but they do try to find the most relevant things for their client in order to help them on their way. All right, and now finally, we said Komodo was a functional API. What we mean now, it should be clear, like, we're trying to provide access to information or expertise in the form of functions rather than the underlying data or objects themselves. And the hope is that this will be a much lower barrier to entry into getting started with space weather, in our case, space weather libraries and models and data, and doing this in a mostly self-describing way. So we're going to try to stay at the high level of functions and just look at, like, say, the documentation of the function to describe what's going on, or be able to see the units and all sorts of things like that. We're trying to do this in a way that produces almost no side effects. So one feature of functional programming you'll hear, functional programming techniques are something that we're obviously going to rely on, is that you try to represent the core aspect, the core, like, nouns you're working with are functions, and that those functions are sort of isolated from the outside world. And so when you call a function, it should basically work the same no matter how many times you call it or where you call it, with some caveats, like, for example, caching, or, like, there might be files that need to be opened in order to call this function. Like, all of that stuff are technically side effects, but for the end user, we're trying to say that basically they can think of it as a black box solution. And yeah, I mentioned it's amenable to functional programming techniques. Now, this is definitely one area where like Python development is, like, technically able to do functional programming, and we've sort of shoehorned things into Python that traditionally people don't use. Like, we've had to, like, redefine certain things just to make this happen. But yeah, basically Python is a more object-oriented paradigm, or it's used often in an object-oriented fashion, whereas we're trying to work at this functional level, which requires us to kind of abstract away a lot of the stuff you would have approached from an object-oriented level. That being said, like, when we're working in Komodo, we are using objects, we are defining our own classes, we are doing all that stuff. It's just that, like, the end user, once we've done all the heavy lifting, the end user can just think in terms of functions. And then finally, this approach is compatible with machine learning and AI techniques. So you can actually think of, like, machine learning as a process of taking raw data and functionalizing it. Basically, I don't really have time to go into how ML works, but I think that there is some nice synergies between like what's going on in the ML world and what we're doing in Komodo. And it's actually kind of hints to like a promising future in and how we're able to like apply ML techniques to functionalize functionalized things that we've brought into Komodo. All right, so I'm gonna pause there and look at the chat because I'm sure I've missed quite a bit. Or is there anything I should know about in the chat before going to the next lesson? I'm trying to get to my.
Yeah, you do have one question in the chat.
One question. All right. It's just every time I hover over the bottom of the screen, it's like not letting me click on it. Okay. There we go. Can you calculate derivatives with uploaded simulation data? If yes, can the user specify the derivative method? Can I personally? Yes, but this is where like we'll get to later, like how you functionalize the simulation output and the tools that we're using such as what specifically Senpai, you can do derivatives and things like that. And it's essentially, yeah, for a non-uniform grid. So those come down to like the details of how you commodify a resource. So one of those things could be like defining derivatives. And what, like if you think of in the functional programming style, basically you can have functions and you can have functions that create other functions. And derivatives are one of those things that create other functions. So you could define your own like derivative operator that takes a function, returns another function. And same with integrals. And it's basically up to like who wrote the data access part of the commodifying process to decide what gets implemented and what they illustrate. And specifically in non-uniform 3-grid, yes. So like what we'll see is that how you you can use like an octree grid or any of those things. Like that all depends on the file format and the data structure of the underlying in our case like space weather models. However, like the people who are best suited for writing those interfaces are either the model developers themselves. They already know how to interpolate the data onto their grid, and all we just need is their interpolator. And so that the end user doesn't need to even see like how you're traversing the octree grid in the case of like that's or us. So yeah, it's definitely a sort of a grad student type thing. Yeah, so I actually did this for ARMS once upon a time, and that's a solar. I think that's the one Savina worked on. And yes, yeah. So I traversed their lovely octree grid, and I created an interpolator for it specifically so we could do like this type of stuff. And it's definitely kind of a graduate level / postdoc style work. But once that work is done, everyone else can access that. You know, just having that interpolator lying around in some Python library is incredibly useful for the community. It's just like, how do we communicate that to the end user? Like, how do we get it into their hands? That's the challenge. All right, so I'm going to go on to the next lesson. Yes. All right, so okay, so this section is just going to be about how we start thinking about functions in Python in a more math sense. And so yeah, I'll just jump into it. So functions may be represented by many implementations or expressions, and you can think of them as like the right hand side. Like think about the right hand side of a function. That's what we mean by like the implementation or the expression. So it could be a code block or it can be a literal like LaTeX, as we'll see later. So let's start with like a simple LaTeX expression that we want to functionalize. So if you look at the cell, you can see like this is how you write something in LaTeX. And this is a good place to start because like everyone in science uses LaTeX for all publications, as far as I know. There may be something else that people use that I just don't know. But this is one thing is like the syntax here, like this little caret thing is how you represent the power symbol in LaTeX. And as a mathematical language, LaTeX is not completely as rigorous as some other languages might be, but it's generally thought of as it's meant to be a typesetting language, not a mathematical language. But there are many libraries that make use of LaTeX expressions in order to do other things. Well, specifically, Senpai is the one that we've sort of built on for Komodo. So Komodo offers some simple tools to turn this function, this right-hand side expression, into Python functions that we can operate on with numerical data. And as I mentioned, like we're doing this with the Senpai library. So the Senpai library is basically, if you click on this link, it's it'll take you to the page. But basically, Senpai is a symbolic processing language built in Python and used by mathematicians. Actually, that's how I first learned about it. I met a random mathematician in Colorado, and he's like, "Hey, you need to look at Senpai for what you're doing because I see where this is going, and this is going to help solve these problems." So you can think of it as like Mathematica, but in Python. It's definitely not as heavily used as Mathematica or as easy, but it is certainly very powerful. All right, so the first thing we're doing is we're going to parse this expression. And you can do that from pulling this function out of the Komodo library. So first thing we do is we define an expression by taking that string that we had before. This is the same as the string. We take the right-hand side of that and we stick it in this guy and enter. And if you put this expression thing on a line by itself, it'll render as LaTeX in a Jupyter notebook. This parse expression thing, we can also pass it straight Python code. Python expressions, not code, not yet. So remember how I said this caret thing represents the power symbol? Well, in Python, if you want to exponentiate something, you use double symbols. I forget what those are called. But yeah, you get the same result. So this expression and that expression are the same thing. And this is like, this thing is the primary tool that Komodo uses to manipulate and inspect user-defined expressions. There are a lot of things you can do with expressions outside of Komodo. So this is kind of a basic intro to Senpai in that sense. But basically, like one of the things you can do is substitution. So you can take that expression and you can substitute the variable x for the variable y, and this will convert that into this guy. You can also substitute other expressions. So here we'll put in y minus 1, and you get the appropriate expression. You can also analyze these things. Like we'd see like what are the free symbols in that expression. So what are the core symbols being passed around when you, and as your expressions get quite large, or if you're doing any kind of programming with these expressions, this is often one thing that you'll need to do. Basically, this returns the set of symbols inside of there. Solutions. So you can solve this expression for f of x equals 0. So basically in Senpai, an expression is already sort of assumed to equal 0. This is sort of something that mathematicians do that might sound really annoying, but is actually quite a powerful way of looking at expressions. So when we want to solve this, all we have to do is call this solve operator, and we tell it which symbols we're solving for. In this case, the symbols operator just returns a symbol. So let me show you what that means. So if we do this, it just gives us the symbol y. So it's basically saying find x in that expression and solve for the expression equal to 0. And what comes out of here are these two objects, these two zeros. So this is the first 0, and this is the second 0. Does anyone know what these two evaluations are? Can anyone guess? I can't hear anything, so Julie, let me see if anyone wrote in the chat. The roots, but what are the numbers? Does anyone recognize what these numbers are? I thought there would be more. Yes, yes, they are this is the golden ratio. The roots of this expression are, this is one of my son's favorite numbers. He knows like 30 digits of this number. But so yeah, so you can take these zeros, and when you evaluate them, so you have this evaluation method basically computes this to a certain number of digits. We can actually evaluate this for an arbitrarily high number of digits, which is something that's really cool in Senpai that is hard to get elsewhere. But so it's like we can put in like 300 in here, and it'll just give us like 300 digits of this. I had to do this because my son was memorizing pi. He has it to 50 digits now, and I couldn't figure out how to actually get, like, where do you find that, the 50 digits of pi? And I ended up using Senpai to solve that. Yeah, the dude's a baller. So okay, what are these expressions? Like, how do we we can use the Senpai's like srepra method in order to see like what's inside of here. So when you call this on an expression, you'll see that it breaks it up into these things. So this addition thing, this power thing, those symbols that we saw, this integer, like these types are basically, so like an expression is composed of these kind of subordinate types. And each of those types, Senpai can reason about. So under the hood, these are all objects, like object-like things, like everything in Python. But for the end user, it just looks like, you know, a simple set of things. So you can use these type things to march through your expressions and reason about them. So Senpai has a lot of other tools for manipulating these expressions, and they're definitely worth looking at, especially if you want to contribute to Komodo. So because, yeah, so I think we're mainly interested in like just turning these expressions into numerical, like method, like basically automatically convert from these to numerical methods or functions that can handle things like NumPy arrays. But like the real power of what we're doing is just by building on Senpai. And you could roll your own version of Komodo by just, if you understand Senpai well enough and you understand like types, like you can do this. It's just turns out it's like all undertakings, it's easier than you think, but harder than you can imagine, because like you don't know what you don't know until you try. Anyway, this is a food for thought. All right, so Lambda expressions. All right, so I mentioned like once we know which variables are in an expression, we can convert these into Python functions that will actually operate on numerical types. So Komodo uses basically Senpai's Lambdafy operator to convert expressions using their free symbols into functions. So out pops this function. It's this is the repro for it. It's very ugly. Doesn't tell you what it does, but if you look at the help for this function, it shows us in the documentation that it is, you know, it's this expression, and this is the actual raw source code for that function. And this is a very simple Python function. All it's saying is just take that thing, square it, and subtract x and 1 from it. So we can test that this works. So we put in 3, we get we can evaluate f3, and we can check that the result matches what we intended. But note that this function is optimized to work on arrays. So, I mean, it's a relatively simple Python expression, but because these NumPy arrays, because the NumPy array data type is amenable to algebra, the lambdafied expression also works. And we'll see in the next lesson about how types work. Yeah, so essentially, like once you've got this ability to work with expressions, you can do kind of sort of more serious science with this stuff. So this is a giant array of 1 million points, and it can do this quite fast. And you can do this even faster if you install the numerical expressions library, but don't do that today because it causes some bugs in in the next lesson. Yeah, numerical expressions library is super awesome. It's faster than NumPy, but yeah, there are a couple caveats for using it. So Senpai under the hood will basically default to NumPy if that's installed, and if numerical expressions is installed, then it'll use that as well. All right, let me check for the. Nope. All right, so. All right, finally, we know enough to talk about the Komodo class. All right, so yeah, for all the talk about functions, Komodo is, obviously it's a object-oriented, like its implementation is object-oriented. And that's partly because I didn't know about functional programming when I started writing it. Theoretically, you could probably do this all with pure functions, but I have not done that. So, so the Komodo class is you can think of it as a container used to register, manipulate, evaluate, and plot functions representing scientific resources. And by container, I just mean like a glorified dictionary, essentially. That's Komodo, in fact, inherits from the what is it, super Komodo class. What is it? It doesn't say here, but basically it inherits from user dicts. It's a dictionary, but with some fancier methods on top that let it reason about expressions. So, so we had that that function before. Here's how you would register it in a Komodo class using dictionary notation. And then when you put a Komodo object on a line by itself, yeah, we'll talk about units in a couple lessons. Can you? Yes, you can do this. We'll talk about this in when we get to composition. So, all right. So, suppose we have yeah. When you put a Komodo object on the line by itself, it'll be rendered like with the LaTeX. So, if we want to access this function, we can use dot notation. So we have that Komodo object that we created here, and we can do just .f, and we can check that this gives us the right result. And these work with these work with numerical data types, so we can stick in like large arrays, and these can have any shape. We can reshape this to. Does that work? Oh, zero. Yep. So we can pass in different shaped functions and different shaped arrays as types into this function, and it'll still work. Sorry, I just zoomed in on accident. I heard. Yes. All right. So we can also register functions with dictionary syntax. So we've got this Komodo object. We can just add a new function to it like so, and it just gets added to the list. So now we have f of x and we have g of x and y. We can add h, and this gives us a third function to deal with. Let's see, anything else about that list? Yeah, there's, I'll get, yeah, so For the most part, Komodo is agnostic with respect to data types. This part of the tutorial is what breaks if you installed numerical expressions, and it may be, I think the old version of Komodo might have some bugs, but just tell me in the chat if you see them. So when I say agnostic with respect to data types, I mean that like Komodo doesn't know or care for the most part what types are being passed around. The type validation is left up to the function implementation. And that's why the numerical expressions library raises issues, because it implements functions differently from the way the Lambda thing with NumPy works. So the exception to this, when Komodo starts to care, is when it comes to the plotting stuff, which we'll cover later. So for the most part, we try to not tell the user what types they can use. So for example, if we put in, so this function f, recall it squares the number and subtracts some things. If we try to pass in a string, we get unsupported types error. And so we just say, oh, you can't do that. But we didn't say that you couldn't do that. It's the function that said you couldn't do that. In the sense that Komodo didn't know that that was a problem, that would be a problem. So the string type throws an exception because f uses a power function, which does not support strings. So however, look at function for g. So if you put in these two words into the values for x and y, you get this sentence. So the reason this works is that string types are okay for g, but not f, because we're only using the add operator, and that actually works on strings. It just, when you add two strings together, it concatenates them. So similarly, multiplication happens to work between lists and integers. So if we stick in the integer 5 and the list for here, we get wow. But this was sort of a coincidence. Like, this is quite flexible, and however, like, you should try to use numerical data types when you can, especially when units come into play. So like, you could be passing around cats and dogs that are implemented with like addition, like in Python, you can write any class that implements algebraic methods. And if you did that,
you, Asher.
Yes.
Go ahead. Oh, there's a question.
For data evaluation, people are getting errors. Try k.f of hey, that part.
Yeah, so it sounds like that you didn't it most likely you didn't did you install the latest version of Komodo? The pip install thing? For those who are getting that error, did you do this step that we mentioned? Pip install Komodo upgrade. Did you do that?
Maybe not. We're working with them now. Thanks, though.
Yeah, this is, so this is the numerical expressions issue. You've installed the numerical expressions library, so you're getting numerical expressions bugs. Yes. Yeah, you need the sorry. You need the -y because oh yeah, I already uninstalled it. But yeah, that -y is important because in the notebook, I don't know if it works in Jupyter Lab, but I often have trouble. Like if I type in a console thing and it asks me something, then it's like it just pauses the yeah. I lose control. So let's see, are there still yeah, so I think that was the bug that I was seeing, and that's why. All right, I'm gonna move on to composition. Okay, so this is where Komodo actually starts to become useful, like doing things that are slightly more difficult to do without it. So the Komodo class will automatically compose functions if it starts to see, if you start using symbols that are previously defined. So, so like we're just gonna make a fresh Komodo object here, and we're gonna create a function g that's a function of y, and this function of h, we're gonna say like take g and stick f in it, and let's see what happens. So it created this new function, g of f of x. And it says, okay, that's what h is gonna be. And the important thing to note is that, like, so Komodo first, it detected that the user used this f symbol, which was previously defined. And so it composed the function, and it also determined that h, this new function, has to be a function of x through this composition. So down here, h is now not a function of f directly, or it's actually, well, indirectly a function of x. So this is how we're able to, like, you can essentially use this to change variables from one thing to another, and you can also, we'll see later, you can do things like coordinate transformations and all kinds of pipelining just through this one mechanism. Like, you could have easily written this yourself, but when things start, when you start bringing in other libraries and things that are all have their own implementations, this turns out to be like an extremely powerful tool for creating these pipelines. So let me read. Yeah. All right. Does the LaTeX rendering only work in Jupyter Notebook? It will not render in a I haven't tried rendering. No, yeah, it doesn't render in the terminal. Actually, while we're on that subject, like other ways to render what's going on. So you can use this detail method, and that shows you like what's in that object in a pandas data frame. So we'll get to these units stuff later, but basically it says like, okay, here are the symbols associated with each of these functions, and here's the left-hand side and here's the right-hand side if there is one, and then we'll talk about units next. But there's also this lovely LaTeX command. Wait, yeah, this is another way to get at the LaTeX with this function. So if you want to grab that, and it has two different modes, and yeah, you can read more about the help there later. I should also say, like I mentioned this in the chat here, but like the latest version of the Komodo core documentation is hosted here on Ensemble's github.io. So like so there's two parts. What was maybe confusing from the notes about Komodo is that, like, where do you go to actually find Komodo? So officially, like, there's the NASA Gov Komodo page, and that's for focusing on readers that are for space weather. But the Komodo core library itself, the thing that we're using in this tutorial, is hosted at Ensemble's GitHub. Sorry, GitHub Komodo core, which is here. And so this is a dependency for the NASA stuff. So at the end of the talk, I can come back to this, but I just thought I'd mention if you're having trouble understanding stuff, this is all. That's your reference for things like this. And then let me look at the chat. It renders in IPython. It does. Oh, I didn't know. Yeah. So yeah, Rebecca's from. I don't know if she introduced herself before, but at NASA CCMC, and she's one of the principals in commodifying space weather resources there. So she can always answer your questions. Okay, so units. We mentioned earlier, this was asked earlier, like how do you attach units to, and how is this related to AstroPy? So in Komodo, units are strictly associated with the function's metadata. Units are not attached to a type. So in most other libraries, units are really a type that you associate with the data and not with the functions themselves. And the reason with that is, this was really a to-do for me, but I'll just do it now. So like, so in AstroPy or /Senpai, units they're kind of a wrapper around the NumPy array. But since we already started out with trying to be as agnostic as possible with regard to the types, we can't really enforce, or we try to avoid enforcing the types at the function level. That's up to the end user of the library, it's up to whoever implemented the function. Sorry. And especially since we may be like, Komodo is so general that it may not be working with, scientific data at all. It could be working with like barrels of oil or something. And those just don't fit nicely into the AstroPy kind of paradigm. And we did try to look at Pint as well when we first started out. But then the other reason is that Senpai already has a unit system, and it's a very powerful and flexible one. And so it's sort of like, if you already built on one library, why complicate things, especially if it doesn't fit kind of the use case. That being said, like you can convert from Komodo units, into AstroPy units or out of AstroPy units when you're dealing with Komodo, and we'll actually see that in our Senpai tutorial at the end of today's lessons. So, and also Rebecca has written a lot of tooling to go from AstroPy units to Komodo and back. So she has resources for that as well. So how does unit registration work? So the way this works in Komodo is we use bracket notation at the function registration time, at function registration time. So this is like a common way that you may not have often seen like units stuck into the argument for a function, but you've definitely seen like on the left-hand side, like what the units are that are associated with the right-hand side. So this is how we write that in Komodo. We basically say like, the user can define what the units are going to be for that expression in the algebraic example. And what this means is like when X is given in centimeters, I promise to return results in kilograms per meter cubed. And this is like a promise made by the function f of x. So like, and that's, so like, it's really kind of a trade going on here. Like this function's like, I don't know where the data comes from. I'm just saying like, if you give it to me in centimeters, I'm going to return the results in kilograms per meter cubed. I'm going to do what I need to do to make that happen. But you've got to, meet me in the middle here. That's basically what this function is saying. And so we can identify the units easily by just looking at this expression. You can say, oh, it's pretty clear what's coming out of this function is this. But if we want to do this kind of programmatically, we can access these units through the meta property of the registered function. So the meta attribute of the function f. So in here we see like, oh, there's units of kilograms per meter cubed, and this is a string. The argument units are also given by a string, but it's now in a dictionary because these functions, we can have many different arguments to a dictionary, and each of those arguments can have its own different units. So I mentioned before the detail method. This is where those units show up. So we can always use, we can parse this if we want to programmatically go through a Komodo object's units. So yeah, up till now, this is just sort of like, oh, it's metadata. Like, how does this actually use? Well, first, in terms of evaluation, nothing changes. So like the only difference is that now we know like that the output must be in kilograms per meter cubed, because that's what the function's metadata said. So like this is the same, this is the same expression that we had before when there were no units. But now what this means is that like, well, the input must have been centimeters and the output must be in kilograms per meter cubed. So far, nothing has changed. Where things start to get interesting is in unit conversions. So remember I said that Komodo can do automatic composition. Well, that's the step where Komodo also recognizes what's going on in terms of the function's units. So it identifies any pre-registered functions. We saw it do that before, but then it inserts appropriate unit conversion factors into the user-defined expressions. So in this case, like the user is saying like, I want to register this function. On the left-hand side, like I want this to happen somehow. Like on the left-hand side, I want to send in meters, like on the function, I want to send in meters and I want what comes out to be in grams per centimeter cubed. And on the right-hand side, I'm saying like, take F and just do that somehow. So Komodo's like, okay, like you use F on the right-hand side, and I looked that up and I saw that it has centimeters and kilograms per meter cubed, and you're asking for this stuff. So if that's going to happen, I'm going to have to multiply your input in centimeters. I have to multiply that by 100 to get it into, all right, so your input in meters that you're requesting, I have to multiply that by 100 to get it into centimeters, because that's what F expects. And whatever comes out of this function, I have to now divide it by 1,000 in order to get from kilograms per meter cubed to grams per centimeter cubed. And then, yeah, I just basically stated what is said here. So this is what G's promises. It's like this new thing G, its role, its raison d'etre is to do what the user said it should do, and in order to do that, it needs to take this form in its final expression. So since the conversion, okay, so two things, like the conversion factors are clearly visible in the generated expressions. So this unit conversion is explicit. And that way we can pair these results. We can easily compare these results with like what we would do in the back of an envelope. So like this is how a human would write it on, on a napkin. And this is what Komodo is doing. So Komodo is not, it's when it evaluates this function, it's not going to, that is when it's going to do this multiplication and division. It's not going to do it to the types like a priori. So anyway, this may seem like trivial, but this really becomes crucial, especially as you involve more, functions and scientific resources, because basically all the data that we're going to be working with has units, and it becomes, the more time you spend trying to get things into your particular unit system, the more you realize that like it's super easy to make mistakes. And so Komodo is sort of there to help like minimize the mistakes that you make. So in this case, like we created a new function H, which is some complicated combination of these two functions. And Komodo was able to figure out that it needs to insert these conversion factors in order to make this happen. Spectral conversions, temperature to EV. So I don't think so. I think the way you would handle that is by defining like a relationship between temperature and energy, because you need Boltzmann's constant, I think, to go from one to the other. So this handles almost all cases. Like temperature is like the most annoying unit in physics, I think, because it's like the one area where it's like you want to convert from Celsius to Fahrenheit, you have to add in a factor instead of just multiplying by a factor. And then secondly, if you're going from electron volts to Kelvin, there's like a Boltzmann constant, I think, that you need to stick in there. So those would be the two things where you have to actually write out the expression, and Komodo can't automatically figure it out. Although I've never tried. So, all right. So now Komodo will raise a name error if you try to do something with units that don't make any sense. So like in this case, I'm trying to register this new function f2, and I'm asking for the input to be in kilograms, and I'm saying like take f and figure out how to do that. Well, Komodo complains that like I can't convert from centimeters to kilograms. That's not possible in our universe. So and this is not possible because it's all, f of x requires x to be in centimeters, and you're asking for x to be in kilograms. All right, so how this actually works, if you're curious, Komodo basically contains its own unit registry for each Komodo object. So when you create a Komodo object, it has essentially a dictionary, which maps, and it's a directed acyclic graph that maps from a function symbol to Senpai unit. So on the left-hand side, you have a function symbol, and on the right-hand side, you have the unit. It's a graph because like first it says f of x is mapped to first a centimeter, and this centimeter is a Senpai unit centimeter. And then it's saying like anytime it sees like this f of a centimeter, it knows that the result should be kilograms per meter cubed. So that's how this works. These f of 2 should not have appeared because like this seems to be a bug because we had to register this and it failed. So it shouldn't have stuck this in here. So this is a bug. We should probably file a bug report at the Komodo GitHub repo, Komodo core repo. So when Komodo encounters an expression containing known symbols, those symbols are paired with corresponding unit, and the final expression is converted to the target units. All right, so here is an example of unit conversion applied to like gravity. There is a bug in function registration for Komodo that we can look on here, which explains like why like we can only do this with 2 variables at present. I don't think this bug has been worked out, but I have checked. So what this is doing is saying like, okay, we're going to have this expression for the gravitational acceleration, and it's going to take mass and it's going to take a radius, and where this mass is the mass of our planet or any gravitational body, and the radius squared is the distance from that center. And we're saying that if you give us this expression, then we're going to return the result in meters per second squared, provided that you give the mass in kilograms and the distance in meters. So this is standard SI units. All right, so we type this in. If we put in the mass of the Earth in kilograms and the radius of the Earth in meters, we find that the acceleration at the surface of the Earth is 9.8 meters per second squared. But now let's say someone comes along and is like, hey, I don't want to use SI units. I want to use CGS units. So I don't know how to compute gravity, but I do know that I want the result to be in centimeters per second squared, and I want the input rate to be in centimeters and the mass in grams. So Komodo's like, all right, if you want to do that, you first have to divide by we're going to have to divide by 1,000, and we're going to have to divide the radius by 100, and then multiply the result by 100. So here we use this G2 subscript to differentiate it from the original gravity thing. But this is kind of illustrating the point that like different communities have different standards for for the units they choose. And you know, you might think, well, why don't we all just use MKS? And that's a long philosophical debate, but the fact is not everybody uses the same units, and they're going to continue to do that for the rest of the time. I don't know, but until everyone uses the same units, this is how you could use Komodo to work in your preferred unit system, regardless of what units the original data or scientific resource is in. And hopefully this is going to at least reduce the number of errors people make when they produce scientific results. So I'm going to pause there to see if there are any questions about units, other unit questions that are going on. Okay, so going pretty well. How are we doing for time? We're just smashing through this. This is 8:30 my time, so yeah, we've been at it for like an hour.
Yeah,
this is a good.
Our next break would be at 3:50 our time, so in like 10 minutes.
Okay, cool. In the H-defined PVC, shouldn't it be x squared? See, I'm looking at Claudia's question. H. Okay, here you said, should it be f squared times 1e to the fifth x? Okay, f is in centimeters, and h wants x to be in kilometers. And we multiplied by 1,000. Just see what you mean. At first glance, it does look like you're correct, but I'm not sure why it's. Oops. Oh, this is what I redefined your K was. This is a good. All right, I'll look at this during the break, but I thought I checked this before. Let's see if it actually. I don't know if it like squared it. Yeah, I'm not sure. Oh, wait. Yeah, no, I'm not sure. Yeah, we can check. That page. So what should have happened is we can assert. So let's see, should we print? Oh, that's a good. Let's see what happened. H of kilometer. H of x is h of kilometer. Ah. Yeah, so, okay. This is a good point to, assuming this bug is correct, we can go to Komodo 4 and we can create an issue. So if you see an issue with Komodo, create a bug report, and this will explain like all the steps you need to do to create one. In this case, it's a registration error. Let's see. There's several different types of bugs, but one type that is this kind of fits in is registration error bug. So you could say like conversion does not work as expected, and then you can stick in here like the details. So yeah, fill that out. That'll help us enormously. One of the things that we like to make sure you do is create some code that yes, define like a test that illustrates the bug. So in this case, like there's a problem registering the sign function. So you would create a Komodo object, assign it here, and then check whether the assertion held. And that's because we stick these tests are what go into our PyTest like test suite. So whenever we update, like, do bug fixes or anything, we need to we have like an automated test suite that will verify whether the change was actually where the bug was actually fixed. So anyway, that's a good place to do that. Doing that in real time here is going to be annoying. So, all right, any other bugs on this? Okay. It's like sometimes someone will point something out and I'll be like, oh, and I try to go through the math and it just takes me time to sort out whether it actually is the problem or if it's behaving as expected. But it seems like on first glance it looks like there's a problem. Yeah. All right. I think we can actually pause early because the visualization stuff is gonna take a bit of time to go through.
Okay.
So
sounds good. I'm gonna steal the screen share back from you.
okay.
All right, everyone. See you back at 4:05. I'm asking you again.
How does this sound? I'm outside, a bit quieter sometimes.
Hey, sounds all right for the moment.
Were you ready to start or?
Yeah, 1 second. Okay, go ahead whenever you're ready, Asher.
Okay, just gonna get some water, but that's good. All right, let me share my screen. Okay. So there were a couple questions from the chat. One was, can Komodo handle Greek, basically? And yes, Komodo speaks Greek. You can put in any kind of expression with Greek symbols, and it'll return, it'll render that, it'll recognize any of those symbols and replace them with log-text equivalents. Basically, you just write in the Greek name without the slashes, and Komodo should pick it up. I haven't tried this with LaTeX expressions, but that might be worth. You put in like alpha. What happens? Yeah, it doesn't like slashes. So so that's cool. And there's actually we have a site, part of our documentation describes like some of Komodo's LaTeX conventions. So we mentioned Greek letters, but for instance, if you want to capitalize a Greek letter, you have to use all caps. Or, well, you have to use either all, you have to use camel, I don't know, normal capitalization. So in this case, like gamma was capitalized, but alpha and beta were not. So you're gonna have to be careful, like where you stick the capitalization. Underscores and superscripts, those are used to define, or subscripts and superscripts are based on whether you use, are chosen based on whether you use a single underscore or a double underscore. So like x sub I, you'd write this way. And then things like, so some symbols you want to put like a plus sign in or a minus sign. So for that, you have to actually write out the word plus. So like in this case, xi plus 1 is how you get this symbol. I mentioned the underscore. And then left and right are used for, like if you, a lot of chemistry notation uses parentheses for some strange reason. So if you want like to represent this species, you would put like O left 3 right, 3p right, and would stick the 3p between the left and right ones. And then finally, for derivatives and stuff, you can use prime notation. So you just put prime in there, and it'll stick that in. I learned recently that you can use bold fonts with BM. So that gives you like a G, that's a thicker type of bold font. And vectors. So you'll see these later in the lessons. But for basically, you just put vec after the symbol that you want to put the vector over. So like fvec, rvec, and that's very handy for hinting at what, indicating to the end user, like what exactly is coming out of this function. The same with hat notation, you can use b hat. There's some other things about like variable reuse that you might want to read here. The second question was, so I made a, the unit conversion bug. I created a bug report for that. And so this will assign this to one of the developers on the project. And then there's that gravity registration bug. This may have actually been fixed in the current version of not the current released version, but the version that's in the Git repo. So we should be able to push out bug fixes for these two things for that. And then this second half of the lesson is more about applications. So this is where we get into commodifying actual models and data. And but before we do that, we need to talk about visualization, which is another area where Komodo kind of works differently from most packages you might be used to. So I think I've addressed all of the open questions. Just check the chat. Yeah. Okay. So first, I should mention that Komodo uses Plotly to handle most of its graphics. This allows us to generate, figures inline for Jupyter notebooks and produce like what we call publication-ready graphics. But more, the primary reason is that Komodo sort of focuses on web readiness as well. So we want to be able to drive web-based visualizations in real time. And for that, we needed a strong JavaScript front end, which Plotly is very good at. So, however, like the way, when I show you like how Komodo actually does plots, you might realize that it's relatively easy to swap out like Plotly for Matplotlib or some other graphing library if you so desire. So it's just a matter of like who actually does that, who implements it, and who wants to pay for that. So Plotly itself, though, Plotly is built on React.js and it embeds D3 charts in the browser. Plotly supports backends targeting Python, R, Julia, Mathab, JavaScript, GDPod, etc. So visit the Plotly website for more info on that. That being said, let's jump into like how we actually use this. So Plotly itself uses these things called graph objects. So here's a very simple graph, like the hello world graph. And it's very data oriented. So you create like, for instance, the scatter plot, you use this scatter object initialized with X and Y values and then a layout, which lets you set the title and many other things. So the nice thing about these graphs is that they're all interactive. So you can zoom in and this interactivity extends to like dashboard design. So Plotly Dash is very useful if you want to like do data-driven dashboards or user-driven dashboards, where you like as the user interacts with the site, it updates the data in the plots in real time. So there's a whole like full stack kind of framework you can build with just Plotly and Dash, and it allows you to basically work in Python for as long as possible. There are a couple of things that are easier to do with JavaScript using their JavaScript library, but for the most part, it's pretty robust. So what I mentioned this like it's these objects are what Plotly objects are essentially data heavy in the sense that what they are, you can think of them as dictionaries of various numerical types or Plotly types. So in this case, like the figure thing that we just created is just a scatter object that's includes like the data, and then the layout is similar. So these things are passed to the client through JavaScript, and I won't bore you with all those details, but like essentially that's it's relatively easy to like set up a plot when it's kind of data oriented in that fashion. So in Komodo, so when you're dealing with Plotly, normally you would have to actually muck around with these graph objects directly, and there's a bit of a learning curve there. It's not too bad, but it's not as bad as like Matplotlib or something. However, you can kind of avoid dealing with the Plotly library itself by using Komodo. So it does most of the heavy lifting for you. Komodo automatically generates Plotly figures from registered functions. And we do this through function inspection. So here's a simple example. We'll create our normal, our go-to function like this. And we can plot it over this space between the zeros of this golden, between the golden ratio, because we know that now the zeros of this function are at the golden ratio, and it creates this nice parabolic function. So, all right, so what happened? How did we do this? So like we just did this in one line. We just registered the function and then we plotted it. The only thing we passed in were the range of X to plot. So what Komodo did was, it's like, first it took that range of X values and then evaluated f of X using that dictionary. So the dictionary we passed in was argument values. And then it determined that the input shape and the output shape of the function were the same size. Specifically, they were both one-dimensional size. So it looked at the input shapes, was that linear array, and the output shape. And then it found a corresponding plot type that matches that shape mapping for those shapes. In this case, it's this Komodo plotting line plot thing. And then it passed the results of the function into that line plot command, and then line plot constructed the scatter object and the appropriate layout, including the title and the axis names. So like the axis was X and f of X axes. And then it returned the Plotly figure object so that it actually shows up in the Jupyter notebook directly. So it did all of that by just looking at the function, inspecting the function itself, which is just this. Or it's inspecting how the function works. So it's still a black box function, and it didn't need to know anything about the types other than the fact that those types had shapes. So if we want to change this, if we want to change any of the properties of that figure, we can use this update layout method. So we can change the title, and we could also change the elements within the plot using this update traces. So in this case, we're changing like the fill to be to 0y, so y equals 0 is up here, and it's filling that with white. So we could fill that with black as well. So this syntax, this update traces and update layout, that's just straight out of Plotly. So any Plotly figure has those, lets you change the properties of the graph that way. So Komodo kind of, after the figure is created, Komodo doesn't really do a lot with the figure. It just sends the data to the figure, and then any kind of customization you want to do, you're free to do. All right, so for step 3 above, like how did it get this mapping? Well, we basically just made up a set of mappings between these different shapes. So I mentioned, so the 1D line is the plot that it generated. So this table shows you like how Komodo thinks about plots. So if you give Komodo a function that has like argument shape, like in this case, it's one variable and that variable has shape n, and the output shape also has shape n, then it's like 1D line. Okay, easy. But then what if it's like 2 variables coming in that have the same one-dimensional length of n that matches the output shape? Then it's like, okay, that's going to be a 2D line scalar thing. And so we have you can imagine there's a whole lot of permutations that you could conceive of, including this thing that we call an image, which I mentioned at the beginning of the talk. Like we can think of images as functions over a pixel space, where the one dimension is n and one dimension is m, and then the output is like some kind of RGB value of shape n m. So we have this image function that generates a Komodo plot. So you see how that works when we get to Senpai later. Okay, so this we can always add to this list. We can modify this list, and you could write your own set of plot mappings. But that approach basically lets us reason about function, like how we might plot something, and it also kind of tells us like if you want a certain type of plot, this is what you would need to do to have Komodo automatically plot it. Like you may not want Komodo to automatically plot your graphs. Like you could just get around with like the evaluation properties of Komodo that we've seen. But this is a way to make it super easy for the end user. So like the end user may not be the one, what we call commodifying your data set. In fact, we hope that they are not the ones commodifying your data. We want the end user to just work at the super high level where they just work with Komodo objects. And if they want to plot something, they just say plot, and then the name of the object. So in this case, like we're making a contour plot with shape where the output is shape n by m. And I'm using these subscripts purely like for syntactic sugar or for just to make it easy to see what type of plot is going on. Komodo doesn't care what the names of these arguments are or the names of your functions are. It just looks at it just analyzes the shape and assigns a plot. So so in this case, it's making this contour plot. Same with vector fields. So remember that syntax page if you want to see how we're putting this vector symbol over here. So here it's making this it's able to draw these vector field lines or these vector field arrows by just noticing that you have something of it a shape n by 2 and it's returning a shape n by 2. That feels kind of like a vector, a two-dimensional vector. So I'm gonna plot these arrows. We can also do that in 3D. So that's what's this? And remember, these are interactive plots. So I'm not sure how the bandwidth is on your end, what you're seeing, but as I'm rotating this and it's smoothly updating the plot and showing this field in 3D. And you can zoom in and out of this and of course customize it. So if you want more examples of like all the rest of the plots, we don't have time to go into all of them, but you can click there and it'll bring you to our visualization page, which kind of explains what I just said, but has more examples. So that's how a visualization works. Let's see. In the next section, we'll talk about commodifying data. Our next lesson, we'll talk about commodifying data and how you're able to how to generate your own quick look graphics so that the user doesn't have to type in anything other than the name of the thing that they're trying to visualize. So let me check that. Just got a message. Here we go. Prepare for 3D. WebGL is not supported by your browser. Are you in Chrome is the best browser to use Plotly for, but WebGL is like kind of the I think it's kind of necessary for plotting in Plotly on the web, specifically because of this 3D stuff that it's doing. You might be able to get away with just 2D, but I'm not sure. Yeah, so try using Chrome if you're having issues, and also tell me what you can also create like a if you're still having issues, please make create an issue on the GitHub so that we can start tackling it. Any other? Oh, try rerunning it. I see that in several internet browsers. You are using Chrome. Are you on a Mac or Linux or Windows machine? Because we've done this on all kinds of machines, so I'm not sure what is going on exactly. But if it's something specific to Plotly, we can kind of maybe push that off to the Plotly side of things, because it doesn't seem like a Komodo specific error if it's really like WebGL. Knows it is specific to Plotly. Yeah, I would bet basically I'd try to start looking at the Plotly community forums, or the it's a very widely used product across many industries. So we may be able to troubleshoot it that way, but we haven't seen that error yet, so that's kind of strange. All right, so now we're kind of getting towards the meat of like why are we going through all this trouble of functionalizing data, and how do we actually functionalize data in the first place? So I've said, okay, it makes it easy to represent raw data as functions by making use. How we do this is by making use of interpolation or extrapolation in some cases. So in practice, how this works. So like, suppose we have some time series data that we want to functionalize. For the purposes of this example, we'll use a fake time sequence. So in this case, we can use like pandas if we want. So we're going to store like some raw data in a pandas series. The next thing we need to do is define an interpolator for this data set. So we're going to call that interpolator row. We're going to actually give it a name that reflects like what is in the literature. So like what in the literature is most closely associated with this scientific resource. And this is like naming a function row is usually like heresy in Python. But the reason you would do it is because the end user is not necessarily a Python programmer, but like a science scientist. Yeah, that's like an Uber scientist. So anyway, density as a function of time, this is what this function returns, and it takes time, and it basically takes that pandas series and reindexes it, and then calls the pandas interpolate method using time, and then this other some other keywords, and then returns the result. So so this type of interpolation, this is like if you're into time interpolation pandas, like you may recognize this. The idea is that the end user hopefully doesn't need to write this themselves. Hopefully, if you're providing them a data set, you're providing them this like a function that has the properties that you want it to have. So in this case, the interpolator assumes the input is a pandas time series. And again, this type enforcement is the prerogative of the interpolator author and is not a Komodo requirement. So now we can plot this data. So to register this function, all we're doing is saying like using dictionary initialization syntax. We're saying, okay, row equals this row that we defined above here. We don't have to choose the same name. We could have called it like row interpolator or something, and then we put or density interpolator or camel case or whatever you want to do. But now, you know, when the end user they see this thing, they're like, oh, okay, that's row T. That sounds familiar. They might look at, okay, what is this row thing? It's density as a function of time. Okay, and it takes by default a date time index. Oh, that's interesting. So like, what if I try to plot this? So Komodo will actually plot it using that date time index that was given in the default value for the input to row interpolator. So this is cool. Like this is a quick look graphic that was automatically generated using the fact that the function that was passed to it had some default parameter for that first variable. In this case, that default was a pandas time index. The reason Komodo can plot this is that Plotly knows about pandas time indexes, and so it can stick in like a nice looking, it can render that time index very well. Okay, and the next cool thing is that like, well, this is just replotting the data that we originally defined, right? This isn't anything new. However, like, let's say we had specific times that were not in that data set. Well, now we can evaluate the density for any of those times as long as it's within the domain of the original data. So this is what this is showing here. So we define 4 different timestamps. This T0 and T3 are outside of the time domain of the original data, and T1 and 2 are inside. So if we call our row function on this data set, we'll get a nan at the beginning and the end, but we'll get values for in between. So yeah, again, this is the original data. So since we did provide the original time index as a default, if we just call row with no arguments, what comes out is going to match the original data set that we defined above. So we can check that like this. We can check that if we call a row with no parameters, we just get back the original data. So so I hope it's clear from here that like this whole process of creating interpolators for data gives us like, it makes the data more useful as far as the end user is concerned, because the end user probably doesn't want to plot things on the exact timestamps that you provided the data from. They probably want to plot density at their own time for their own event, even, you know, space weather event. They may have a range of times that they're interested in. You may have a spacecraft or a simulation that produces results at times over a wider range of data or times or positions. And the end user knows where they want to plot things. They just don't know how to get the data, like at the data at the locations where and times that they want it. So we made the raw data, the original data, I should say, we've made it more flexible, and this allows us to evaluate over new time domains without losing access to the underlying data set. Now, of course, if we want, we can always go deeper and into that underlying data set, like that's fine. But for the quick look graphics side, or for just like finding out what's there, data exploration, we can get away often with this super high level approach. All right, so let me just pause there, because like, as we kind of, this is kind of a very, okay, if I want to produce a plot and save the figure using an example 3D vector plot, how do I do that? So here you can, there's a couple ways of saving the figure. First, you could just download the plot as PNG. You can hover over it and it'll store that, it'll just download it, and it's rendering it at, you know, it's chosen a certain pixel resolution to render this, but there's, you'll probably want to look at Plotly Orca, or there's several different backends for exporting the figure into different resolutions or in different, like a lossless way of rendering. So that's typically how you would save it for a publication. You wouldn't be saving a PNG, but you'd save a, I forget why the extension escapes me right now, but that's how we deal with generating plots. But this is basically, you can also export the figure as HTML. So if you want to include it in a like in a report that you're handing to some client or someone, and you want to keep that interactivity, you probably want to save it in HTML. You can also save it in like a notebook. So this is how we generate. This is how we were able to save these graphs in the documentation for the website. These are all notebooks that are rendered and saved with the data in them. So yeah, there's several options. Plotly Orca is the name of the backend that Plotly recommends. So you can go there for more. Okay, so we mentioned this term Commodify. So what is this like? So how we actually take a simulation or observational data and we make it functional? That process we call commodification, and we most readily do that with this Commodify Decorator. So we mentioned earlier that in functional programming, you have this concept of like taking a function and generating a new function from that function. So decorators are the mechanism in Python where you can easily do this. So with a very compact syntax. So in this case, our Commodify Decorator, it says like, you give it units and you give it other metadata that is expected for this decorator. So like if you have a DOI, you would put that in the citation. And then this is our same interpolator function, but now we're just added this Commodify thing. And this thing is, this new row has in its metadata the units, the citation. There's no expression on the right-hand side because now this is an interpolator. There's no like closed form representation of the data. So when Komodo sees that, it just uses this lambda symbol, which in functional programming represents like an anonymous function. So think of it as like the black box symbol for the function. So yeah, we didn't specify the right-hand side, so Commodify just gave it a lambda symbol. You can click here to learn about anonymous functions. And the second thing Komodo did was it attached the meta attribute and it attached a data attribute. So we saw row.meta and row.data looks like this. So you might ask, like, where did it get this data from? Like, what is this data? Well, the data is the result of calling row with no arguments. So when Commodify saw this function, it's like, all right, I'm just going to see what happens if I call it without saying anything, without providing any arguments. And what popped out was this object. So everything that you Commodify will have a data and a meta attribute. And this was in order to be consistent with PyHC requirements from like 3 years ago, which this may not be a requirement anymore. I think Julie can jump in to tell me if this is a requirement or it is no longer a requirement. I'll pause. So no, it's not, maybe not a requirement, but it is certainly useful. Because like, if you're still not like on board with this idea that you should represent data with functions, well, you can still go back to the data. You just you just call the data attribute and you've got your data. And then you just do what you will with that. And then the third thing it does is it updated the documentation of the function. So now when we ask, what is row, we get this citation down here. We get like we get this updated. There's other things that it will appear here if you so desire. Okay, and then finally we attach this metadata without modifying or recasting the original data types. So in this case, like Commodify didn't actually change how the function works. All it did was attach some metadata to the function, and technically what it really did was create a new function that wraps the old function. So it's meant to be very hands-off with regard to the functions that you create, and allows, but what it does allow you to do is easily register things in Komodo objects. So the next lesson is about commodifying a larger data set. Kind of pause there for any questions. Plotly Orca. I'm going to put a link to that. Okay. So, okay, on to the next lesson. All right, Komodo models. All right, so we saw a little bit how to turn raw data into functions. And while this is a straightforward process, we also don't want the end user to actually do this. We want to do this for them. And to do that, as developers, we want to handle as much of the heavy lifting for them as possible. So instead, what we want to do is commodify scientific resource, which means collect all the prepackaged commodified data into a Komodo subclass. So this tutorial focuses on building like a commodified model from scratch. If you want to see like the full implementation, you can just skip down to the bottom. But now here's where we kind of lay out like if there is such a thing as a Komodo requirement, this would be the list of them. Because we've tried so hard to be like general enough that Komodo does a lot of things without you needing to do a whole lot yourself. So all of these things are things that like make Komodo more useful to you, but we try not to absolutely require them. So for example, like you should probably use a function name and arguments that follow Komodo syntax conventions. We saw the syntax page earlier. That's this page. Oops. No, don't leave. Yeah, that's this page. So when you follow these syntax conventions, it gives you variables that render nicely in a notebook or in a publication. Because remember, like we can always convert, like call that to LaTeX thing, and it'll return us a LaTeX string representing the underlying resources, and then those you can just copy and paste into your manuscript. So when you're like preparing a publication. Another thing you should probably do is provide default arrays for the input arguments to the functions that you're providing. If you don't do that, then the end user is not going to be able to easily plot what you're showing. They'll have to just guess and check like the domain if they want to see a quick look graphic. I just heard someone open the sprite. Yes, Komodo takes expressions written in LaTeX as well. So, yeah, I sort of showed a little bit of that at the very beginning. How, yeah, Komodo, this is a LaTeX expression. So Komodo can understand that and convert it into a Python function. And then this meta attribute, you should probably use this if you want to represent the physical units of the function, both the units coming into the function and the units going out of the function. Your citation information, like how should the scientific resource be cited? Like, how do you give credit to the people who built that, the original data or the interpolating function itself? Like, all of that goes into here so that the end user can easily cite your work. This equation is sort of a LaTeX representation of the model or data source if that's available. This is purely for rendering the output. So instead of that lambda, it would show this equation. So Komodo doesn't use this equation. It would just, it doesn't lambdify that equation. It just simply uses it to replace that lambda expression. Hidden arguments. This is like, sometimes you have a bunch of arguments to a function that you don't want to show up in the LaTeX. So this is how you hide those from the display. And then the data attribute. So this is an array holding the variable if it's available. Sometimes there is no data associated with the function. Like the sign function has no default data to it. It's just like you have to tell it where you want to evaluate the sign function if you want to. And then any doc strings that provide further context. So what I'm going to show you is like what we call like the model reader tutorial. What this is going to do is it's going to simulate opening and closing files. It's going to need to manage some state variables, initialize some interpolators, commodify those interpolators, and register those functions. So why we call it a model reader is that it when we deal with space weather models or simulations, is the other word for it, those are typically things that don't run in like, they're not in the RAM, sitting in the RAM on your machine. They're usually run on a supercomputer on a cluster somewhere, and they dump a whole lot of data to disk in some format. So a model reader, what it does is it provides a Python, it's some kind of Pythonic access to the data, and then it provides interpolation methods for that data. So what we're saying is that, like, if you're going to write a model reader, you should provide at least one interpolation method that satisfies all the requirements that we listed above. So, okay, it's easier to explain with an example. Let me just quickly check. Yeah. So we're going to do some imports. All right, so I mentioned that like this commodifying process starts with like subclassing the Komodo core object. So in Python, when you subclass a model, what you're doing is or subclass another class, you're getting access to all of the methods and and like things that class does, but then you're adding onto it additional features that fit your specific situation. So in our case, like we're saying, like we want to create our model, we'll call it my model. And this thing, instead of just being a normal Komodo object, it's going to actually require a file name and some keyword arguments. So we're just pretending that we're going to open some file. We're going to store that file name. We're going to set some missing parameters. There might be some additional data that we need to store before we can do anything with this with our raw data. So in this case, we're creating, like we're setting up a grid interpolator. So what this is saying is it's using the Senpai Library, and it's plugging in some data. What we're mocking is like density data. This data happens to be a function of these position parameters, but it doesn't have to be. It could just be like a raw output result of a simulation. So we stick that data here. The regular grid interpolator expects, like it's called a regular grid interpolator because it's the data is oriented in a logically regular fashion. So the X, Y, and Z arrays are specified, and those correspond to, in shape, to the full density block of data. So this is just vanilla SciPy stuff. And all we're saying is like we stick that in like we store that somewhere in our object, and then we define an interpolator. In this case, we're just calling it interpolator, and we're saying commodify this thing, give it these units. It's going to take a vector, and it's going to return a density result by calling that interpolator. So we define this thing, and now we're going to register it in the object itself. So I don't know how to split a line, but basically now when we initialize our model, we give it some file. It says, okay, I'm opening a file, and I'm returning the Komodo object that has this beautiful, simple, like high-level representation of the underlying data set. So, and now from here on out, like the end use, this looks like a normal, like all the other stuff we did with just simple expressions, it's the same, but now there's real data driving it. So if we want to evaluate it, we can pass in like an array here. In this case, it's like a list of lists. And this method happens to know how to deal with lists of lists because the regular grid interpolator knows how to deal with lists of lists. So that type enforcement thing, that's applying here. This point is outside the domain, so that gets a NaN. And there's still a problem with this. Like this registered function, it doesn't have any defaults. So if we give this function to our end user, they're going to try to evaluate it, and it's going to be like, hey, there's a required argument here that you're not giving me. Which means if the user tries to plot it, what's going to happen? Komodo is going to complain that it's missing an argument. You need to tell it where to plot. So okay, if you sort of stopped there and you didn't do anything else for the end user, then they're going to have to figure out this stuff themselves. So for generating plots, the user has to already know where they can place the resolution, like where they can plot. For example, they could like inspect the attributes of the model and just sort of guess by looking at the domain. So they may have, so like remember restored the X, Y, and Z arrays? Well, the user might be like an intrepid grad student and they're like, hey, I'm just gonna look around in this thing. I found these attributes X, Y, and Z. Well, I'll stick them in a mesh grid and then I'll generate some points from them. I'll do some like array gymnastics. And then based on this, I'm going to plot this the density at these random points. So in this case, so they're still using Komodo to plot the data. So this is a 3D plot of those points for the density values that they're checking. But they had to guess where to plot them. They didn't know, like, they didn't have a good way of just doing this easily. Now, if that person is a programmer, then this might be easy for them. But if it's for the people that don't have that background or that skill, that Komodo starts to really shine. So, and just hopefully the user didn't choose points where the solution may not be valid. So next we're gonna like modify the function and provide some default parameters. Before I go on, like I hope this was clear, like what we did in terms of the subclassing Komodo, but also like the problem that arose when the user doesn't know where to plot things. Like, are those two things clear? Just someone in the chat can tell me if it's not. Okay. No one has said anything. I will assume that silence is agreement. So okay, what we're going to do now is like we're going to take our original code and make it even more useful. So first thing, we need to include defaults. So in this case, we produced the Commodify model with one variable, but we were unable to produce a quick graphic, which required the user to inspect the model and guess where to interpolate. So how do we include defaults? So basically, we redefine the model, and everything in here is the same, except for one line. That's this line here. This is the only change that we need to make to the model. So what we use is this Gridify decorator. So this is a decorator that ships with Komodo. By adding this Gridify line, we've modified the original function to be one that generates gridded data. And moreover, the variable now has default parameters. So look at the expression now. Instead of, initially we had row of this vector, right? Before we had this xvec thing. And now we have row of x, y, and z. So if we look at what row is, we see it's this thing called row, but now it has an x, y, and z arrays, and these are different shapes arrays. So that's interesting. That means that we can call this without any variables, and it'll return an object, or it returns a NumPy array with the shapes corresponding to what were default shapes. So now if we want to like specify one of those arguments, let's look at what happens. We get, like, if we say, okay, Z is going to be fixed at 8, what comes out is this array that shapes 22 by 11. So, and these are the actual values. But how do we know to choose the plane Z equals 8? Well, here we could actually use Komodo's function inspection to get like the default, to get at those default ranges. So we saw like we could look at the, we could just like stare at this for a while, but there's a better way to get at those defaults. We use the get defaults function in Komodo. So this will inspect a function. Here we'll give it row, and it'll turn the defaults into a dictionary. So just so you see, all it does is like use argspec, and it returns a dictionary with those defaults. So that's super useful if you're doing programmatic function inspection. So we're just looking at Z, we're getting the average of it, and it's returning 8. So this is not specific to this model. Like, you can use get defaults on any function in Python, and it'll tell you something about those functions. So the user doesn't have to know anything about the implementation for a model to do that. Okay, so the final implementation. So now we're gonna make it even more useful for the end user by giving them some hint about what's going on here in terms of like how these functions work. So we're going to add this IJK subscript, and we're going to register a few different functions. So in this case, we're going to create a grid interpolator, which will, like, for a given variable, return an interpolator for that variable. We're going to create a bunch of variables as well. So this is just creating some fake data. And we are going to, just checking. Oh yeah. So this function registers a given variable. I'm kind of just glossing over the implementation details here because it's nothing more boring than reading code, but especially my code. Hold on, my AirPods are dying. I have to switch. Okay, can you still hear me?
Yep.
Okay. So so basically all this setup does is it creates two variables, rho and p, and it defines like what the units are and what the data is for those variables, and both these variables are going to have the same grid. So when the user runs this, they see like, okay, there's this original data in the vector format, and then there's also this data called row, but now it's an IJK format. So where xi, yj, zk are input parameters. So like a physicist or a mathematician looking at this would say like, oh, I think I see what's going on. Like, this subscript refers to the output shape of like this function, what it's returning. So I can pass in different array shapes, and what comes out might have, I can expect the shape coming out of it. And we can turn on or off that gridify thing through this thing. So like if the user doesn't want to see two versions of every function, they can just use this keyword argument. And this keyword argument is only specific to this model. Like, so when they look at my model, the help for that, it's like, okay, we have this additional keyword, we need a file name, and it tells us like, this is actually the help from the original Komodo base class. Okay, so this is cool. So this is a lot more useful for the end user. We made this optional, and this design choice to make like to turn on and off different variables, that's completely up to like whoever authors this commodified subclass. And so this is yet one of those, this is another thing to consider when like designing your Komodo subclasses. Like what is the end user most likely to need? Like you're not going to need it kind of philosophy. Like don't put extraneous stuff in a Komodo subclass if it's just like very specific to a certain researcher. Like sometimes you're just targeting a customer that wants specific variables, so that's all your Komodo subclass should provide. What are the typical names or units used in the literature for your science domain? So be aware of those so that when the science user sees this gobbledygook, they're not just like completely thrown. Try to use that scientist's own literature. Like that's even a great way to be like, I've had some clients where it's like, I just work straight off their MATLAB and commodify that code and give them the variables that they're expecting. Is this resource part of some other pipeline? So like, that's where types come into play. Like if this, what comes out of the Komodo object is like must be a certain data type, that's where you need to consider that. Are there type requirements? And if scientific notebooks exist for a given data set, just start there. Like there's nothing, like notebooks are kind of the go-to thing for data scientists and physicists that are at least the newer ones. And so like they've already done a lot of the legwork for what you need to do to commodify the data source. You just need to build off of what they've already done. That's generally like strategy for all science, like just, rely on the shoulders of those who came before. So, okay, so now that, because like what we want, what the end user wants to be able to do is just like pull data from all over the domain, not just your specific scientific resource, but from other data sources as well. Like they want to do data model comparisons, or and they don't, like if they're a PhD grad student, they might have the time to devote to learning every single library that you can throw at them. But if they're like, sitting on a space weather desk, or like a teacher in high school or something, and like their students are trying to get up to speed, what we're hoping is that Komodo can become one of those tools that just give them the bare minimum that they need, and then they can kind of start learning from there. It may not be there yet, but like that's kind of the future goal, or the goal for the future. So yeah, so you can once you've got like a commodified data source, you can mix and match new Komodo models. So like in this case, I'm making a new Komodo object, but I'm grabbing a function that's already part of some other Komodo object. So now this function, like this object doesn't know anything about the other parameters in model. Like model had like 4 different variables. This one is just a much slimmer down thing, and we can use it and combine it with other things. So like in this case, we're gonna estimate the volume by using like using this expression, like 4/3 pi r cubed. Well, no, it's like it's taking this is not a normal volume metric function, but now we can compute like the density times the volume. So this density is real data and this volume is an expression. And so what comes out is like, okay, I'm going to take rho of x and the volume at x, and I'm going to produce this mass at x. That doesn't really mean anything. It's just like, I mean, it isn't this example is just to illustrate the idea that like Komodo handles this function composition. Someone actually implemented what rho of x is, and then the user added a little bit of sprinkling to create this derived variable, which it just combines the existing variables. It was asked earlier about Plotly Orca. This is where you could, this is explaining how to get at it. Okay, so since we've done all this work of visualizing, we can easily plot like at a specific value, in this case, the average position. So this is kind of concludes how you commodify some fake data. In the next lesson, we're gonna look at doing this with real data. So I'm gonna pause there. Okay, there's no comments. Either we're going really well or horribly. There's no in between. Okay, so lastly, we will look at commodifying real world science data, and we chose for this the Senpai Library because, well, first you've got experience with that this week. Also, it's something we hadn't really commodified before, and it's a very powerful library that is used ubiquitously within the solar physics community. This is our kind of initial stab at this, and it's not complete by any stretch of the imagination, but it does start to show you like why Komodo is useful, might be useful within your community, but within specifically this domain. So I just got a alert. I don't know if that was Slack. Okay, so here's how you would normally work with the sky coordinates class within SunPy or AstroPy. In fact, I actually found that like as I was writing this, that if I didn't add this line, then the sky coordinates wouldn't be able to find the SunPy coordinate frames. Maybe that's just like a known thing, but so here's how you would normally work with this class. We would define a sky coordinate object. You give it some arrays, what units you want the result to be in, and which frame and which observer, and an observing time. And then assuming you know like what the methods are in the sky coordinate object, you can transform to say like the heliographic Stonyhurst frame. And then based on that, you can extract the X, Y, and Z values in Cartesian coordinates and generate like a set of points. So here are the points that come out of here. So what this is doing is it's converting the original arrays that we provided, which were defined up here, from longitude and latitude in helioprojective coordinates from Earth's observer, and it's converting it to these coordinates in Cartesian. So cool. So what we wrote is a Sky Komodo interface that wraps the Sky Coordinates class. It commodifies the Sky Coordinates class. So there's some bug in the latest version of Komodo that keeps putting up this warning, so I apologize for that. Okay, so here's how you would do this with the Sky Komodo class. You initialize it saying like which frame you're going to and which frame you're going from, and out pops this this function. So what it's saying is, I'm going to return you a vector, an x vector, which indicates that it's a Cartesian vector, and I'm going to go from it's going to be in heliographic Stonyhurst coordinates. That's the subscript. And where it's coming from is this HPC frame, helioprojective coordinates. And alpha and delta are kind of classic ways of defining declination and, is it declination? longitude, latitude. And then we can see the units, arc seconds. And then what comes out is in kilometers. So it's that vector, but it's in kilometers. So how do we call this? So we have those original points, longitude, latitude. Oh, also time. And the time is a Unix time. Did I say seconds? This isn't correct. It should be it's not a Unix timestamp. It's like a, you know, well, there it is. It's I forget the name. ISO formatted time. So it should say T ISO and then no units. So apologies for that. So we can check that this matches the result we got above. Like the points that come out of here are the same as the points that came out of here. So basically what we're showing is like all of this stuff. If the end user didn't know it, they could still use the sky Komodo class to get the same result that they would have gotten. And if they want to look at the help for this object, like the sky detail, they can see. And the help is here, converts from Earth helioprojective to Earth Cartesian heliographic Stonyhurst. So it actually dynamically created the documentation for this function to clarify for the end user what this function is supposed to do. This Sky Komodo class, you can use it to register multiple coordinate frames at once. So in this case, it created these three permutations. The reason why there's only 3 is that it skipped the permutation from heliographic Stonyhurst back to itself. So basically, you just put in a list of which frames are going from and which frames are going to, and it gives you back all of the possible permutations. Here's the detail of that. And then I think there's one more keyword argument I wanted to illustrate. Verbose from units, arc seconds to observer. Yeah, that's all for now. But just like, the question of like, is this ugly having both a superscript and a subscript? Maybe, but this is something that, you could put in, like we could put in as a keyword, like hide the superscript if there's only one like frame that you're going to. I actually I may have tried to dynamically figure that out, but yeah, those are all like, that would be a, what's the word? A life, making your life easier kind of feature. I forget what they're called. So that's the Sky Komodo class. Let me check the chat. Oh, okay, 5-minute wait. Okay, cool. Yeah, we're very close to being done. So the last thing we commodified was the sun map object, or the which we're calling the Komodo map. So here's how you would normally work with. Sorry, may need to download something. Oh no, it's already got the data. Okay, so normally you would initialize like an AIA map this way. Here's the location of the image that gets downloaded when you initialize this. Here's how you would use the sun map object. You just give it that string, and I think this is it has to do with the suffix. So like we could put like AIA as the suffix, or its prefix, or the subscript, and it'll stick that in there, or we can do it this way. Just leave that blank. We can, for instance, convert. So what these represent are pixel coordinates. So this image down here is the image over these pixel coordinates. And this is the image over the pixel coordinates split up into latitude and longitude, I guess, or alpha and delta. So And then here we're registering a new function, which is the log of the image. So if we look at their sun map object, the pix log comes out there. So now we can look at, let's plot this for given alpha and delta. And when we do this, so like we're basically saying we want to choose alpha between -500 and 0, and delta between 0 and 500, and we want 200 points. And what comes out is this image of the sun kind of zoomed in at those coordinates. This is not a normal kind of image. This is like using the contouring library in Plotly as well. So it's not how you would normally see this image. We're still kind of playing with how, like, what is the best way to represent image. Like we should probably just have, you know, a normal background image here. But the point is that, like, now that we functionalize things, we can automatically plot stuff in Plotly coming out of SunPy. So SunPy's main, you know, plotting library is matplotlib, and so this shows that you can actually change or choose different things for how you plot. And then finally, if you want to get at the raw, I just forgot the name of it. Is it sun map? Yeah. Oh, so it's sunmap.sunmap, yeah, of course. You can always go back to the raw data set, if I could just remember what the name of that is. So while I look that up, I'll take any questions. Okay, this is the class that I just implemented, or that we implemented. So name, image file name. Okay, so it's just underscore. I left out the underscore. It's always some mundane detail. All right, so if you want to get at the original SunPy map, you can access it this way, and this is how we're used to visualizing the data in the notebook. So this concludes the whole tutorial. This is basically, we've seen like how you go from kind of pure functions all the way to like real scientific data. I hope that this has illustrated why Komodo is useful, or what it hopes to accomplish in terms of like making these libraries more accessible, making the data more accessible to like the average user, and some of the strengths and also weaknesses of Komodo. So yeah, I'm really looking forward to answering any questions now. So there are no questions. Okay, so yeah, I guess I'll stop there.
Thanks, Asher. Any in-person questions? If not, you can always post in the Komodo channel for Asher to look at later. But for now, we will go on to a short coffee break, 20 minutes long. So we'll be back at 5:40. Thanks, Asher.
Thank you.
demande est-ce qu'il y a du son. Est-ce que... Ouais, il y a du son.
In like 5 minutes, can you bring something? That'd be great. Thanks.
Oh, did I miss things?
There may be some mini bits.
Hey, Julie, just wondering about the microphone. Is it on? Is it on? Should we clip it on?
Yeah.
Hello, can everyone hear me? Is it working now? Yes, good. Yeah, so where was I? I was talking about Amda and Cyclop. So yeah, Speasy is a project developed by our group of CDPP, so Center for Plasma Physics Data in Toulouse, and in collaboration with the LPP at Polytechnique. So in both of our groups, we've been kind of doing parallel similar work. CDPP has been developing a program called AMDA, stands for Automated Multi-Dataset Analysis. It's a web application that provides a collection of space physics datasets and tools for visualizing the data, extracting interesting statistics, doing data mining operations and things of that nature. And Cyclop is pretty much the same thing, only it's not web-based, it's a desktop client. It's fully open source, developed with a library called Qt. And they mainly use it for labeling data for machine learning. So whereas Amda is more of a data provider, we have a collection of data sets that are provided exclusively on Amda. Cyclop is more of a client, and it uses in its backend Python modules to access various web services of CDA Web, SSC Web, and Amda, and provide the data in the interface. So that's how we've been developing. I have no physics background. So I tend to view data as the pure, beautiful numbers that they are, without ever trying to understand what the physics is behind it. So when they presented Amda to me and showed all of the beautiful functionality, you can download data in CDF format, NetCDF, CSV, do all kinds of interesting calculations. I was like, yeah, that's great. Give me the NumPy array. I just don't care about anything else. I just want the raw data and manipulate it my way in my Python scripts. So thankfully, Amda does have a web service, a REST web service. And the first step was developing a small wrapper called AmdaPy that has since been depreciated, should not be used anymore, even though it's still available on PyP. And on the other side of the LPP, Alexis Jandet, which is the main developer for Cyclop, developed a little Python module called SPWC, which is just a Python wrapper around Amda, CDA Web, and SSC Web's REST services to list and download all of the data available. So we noticed that there were so many similar functionalities. His code was much better than mine. So we decided to merge, well, rather SPWC kind of absorbed AmdaPy, and it gave birth to Speasy. As I said, it's mainly developed by Alexis Jandet, which he's the main developer for the project. I mostly deal with all the functionalities that are linked to Amda. And of course, Benjamin Renard, who's the main developer of the Amda platform. So the current, it's a very recent project. It's a very young module. So expect to see many new releases coming out soon. And we hope to add a lot of functionality to the module. The current stable release is version 0.10.1 that you can download on PyP. And of course, you can always get the latest version directly from GitHub, although we don't recommend it because it might be unstable. And of course, if anyone encounters any issues with the code, don't hesitate in posting an issue on GitHub. They'll be happy to deal with it, not me. So about the features of Speasy, it's fully open source code. We developed it so that users pretty much only use one function, the Speasy get data function. So it accepts 3 arguments. 2 of them are optional. The identifier of the data set or parameter you want to download, and a start and stop date. So this is essentially for downloading time series data. We also have a couple of functions that allowed users to navigate the products available on the various platforms. So retrieve description information, the global starting and stop times of the data sets, units, and all other fun information. And the other interesting feature of Speasy is the implementation of a local and possibly proxy caching system. So you can define an intermediary server at the level of a lab, for example, or your work group. And every time data is downloaded for the first time, it'll be stored in the caching server so that subsequent download requests will be much faster. And for now, we only support 3 different data providers, CDA Web, SSC Web, and Amda, but we plan on adding more in the future. I also like to say that CDA Web's product inventory is so extensive that we still have trouble listing all of the available products. So the inventory functionalities that I'll be presenting afterwards don't work for CDA for now. So Speasy supports 4 different types of data structures, time series, which are, so everyone knows what a time series is. Data sets, what we call data sets are collections of time series that share a common time base. And timetables and catalogs, which are pretty much just collections of events. So timetables are just a collection of start and stop times associated with an event number, and catalogs just timetables with additional information. So products are identified uniquely on each platform, and Speasy uses a special string for identifying each of the products, which is the provider name, followed by the product ID as it's shown on the desired platform. And they're also represented as a special object called a Speasy index object that you can access through the inventory. I think it'll be clearer when I go through the notebooks. And so down here are some plots. Speasy supports some very basic plotting functionalities that allow you to rapidly check that the data you've downloaded is what you want. So in the future, we want to add more functionalities linked to using Speasy in notebooks. So it's a lot of auto-completion functions, for example, supporting various data formats, adding specific features for each of the web services. So Speasy already has functions that allow users to interact with their own account on Amda. So I don't know if you're familiar with Amda, but you can define your own physical parameters. Speasy will allow you to download them, as well as timetables and catalogs. We want to add more support for plotting and adding documentation and example. That way, we're always happy to have use cases. If you have any interesting notebooks using Speasy, we'd be glad to add them to the documentation. Next, I want to go over the notebooks I prepared. So I have made some changes. We've been worried that Amda's server might crash if everyone does the request at the same time. So if you're using your own Jupyter Hub, you should head to the Speasy tutorial directory and run the pull from remote command in the Git menu. If a pop-up appears saying that there are local changes, you can just discard. It shouldn't overwrite any of your local changes, but it'll pull the latest version of the notebooks. So let me go over to that. So you can just, Speasy is simply installed with pip. You just do a pip install Speasy and you should be good to go. Matplotlib is used for the plotting. It's not part of the requirements, so you may have an error if you don't have Matplotlib installed that was with Speasy. You should install it alongside it. So when you import Speasy, every time you import Speasy, Speasy will query each of the providers for a list of available products and fill the inventory. This is not yet cached, so the import Speasy as SPZ sometimes takes a couple seconds to execute. And that's why we can't implement the CD web inventory, because it's much too extensive. It would take hours to load. So the current version is 0.10.1. You can access information about where the cache files are stored. So I created a local in the GitHub repository. There should be a cache folder that contains, and that's already been pre-filled with all of the data that's going to be used throughout the notebooks. So if you don't have it, the notebook should work. It'll just take a bit longer to execute. By default, the cache size is limited to 20 gigabytes. You can change the settings, the location of the cache, and the maximum size of the cache using the Speasy config cache path get and set functions. So the cache path and cache size attributes can be set. At this point, I also want to warn that Speasy has a configuration file that's stored in your home directory. When you set a different cache size or cache path, it'll change the contents of this file. So any time you import Speasy in the future, it will load the same configuration. This holds true also for configuring your account information when you want to access your Amda account. I hope I was clear about that. So you should just be mindful if you want to just temporarily change your cache location to change it back afterwards so that you don't get errors in the future. It also happens between versions, or if you do some downloading of a very extensive data set, the cache may become corrupted for some various reasons. Usually the best solution is just to destroy the cache, and it'll just get refilled in the future. So we're gonna go through how you can retrieve some data directly from Amda. So I'll go over on Amda. This is what Amda looks like. So you've got here on the left of my screen, the whole inventory of available missions. So all of the data sets are stored on the same hierarchy, mission first, followed by the instrument, the names of the various, so these are the instruments, and then the data sets, and inside the various parameters. If you hover one of the parameters, you'll see a little box appear with an ID. So I don't know if it's very visible on the screen, but for example, this parameter is ID'd IMF_mag. And this is the ID you'll need to use when you download data from Amda. CDWeb's got, I'm sure most of you are familiar with the identifiers on CDWeb. It's pretty much standard. Sorry. I have a question. What data models arrangement of NumPy arrays does Speasy use for data that has been received? I expect this may become clear during the current active demo. Yes, it will. I'll come back to it. So once you've identified the data set you want and you have its ID, you can head over to your script and see I have defined a couple parameters. So if you have the old version of the notebook, there should be a third one. That won't work. Its name has been changed since. Sorry about that. It shouldn't impact the rest of the execution of the notebook. You'll just have a couple of plots that won't appear and an error message that's not to be worried about. So I'm not looking at the right parameter here. We're going to look at stereo magnetic data. So where is that? Stereo A, mag, 1 minute data. So we want, sorry, it's het 1 minute EFL. Go. There it is. The number, you can just right click, plot. We're interested in 2020, so 28th October 2021 for 1 day. Go. Oh. It is not. There we go. So this is what we see in Amda when you plot some data, and we'd like to get the same data in our Python script. So we'll first define the start and stop time. So Speasy is quite flexible. Yes.
Can you just zoom in a little?
On the notebook?
Yeah.
Can I hide the sidebar? There we go.
Great, thank you. Oh,
Oh, come
no.
on. No. Okay, this should be good. Yeah, so where was I? You'll have to define the start and the stop time and the parameters ID. So Speasy is supposed to be quite flexible on the format of the time you pass the get data function. So it can be an ISO formatted string or a datetime object. And then you just need to call the get data function with the 3 different arguments. So parameter ID, start time, and stop time. Now I added disable cache equals true. This is if you don't want to use the caching system on your computer. It's just to illustrate the difference in access speed with and without the cache. So first I'll download the data using the cache. It'll take a couple of seconds. Yeah, so 5 seconds for 1 day of data. I have no idea if this is good or not, but using the cache, because I've pre-filled all of the cache folder, it'll be much faster. So if you plan on using the same data over and over again, it'll be much faster if you cache all of the data on your system. We also have a plan in the future to make Speasy able to work when you're offline, so that all of the data is directly loaded from the cache. For now, it doesn't work because when you import Speasy, it'll try to query every data provider for a list of products. And if you're not connected to internet, it'll fail at that point. So that'll be a future release. So as you can see, it's much faster with the cache. So the get data function will return a Speasy variable object. This is coming to getting to the answer to the question that's been submitted on Slack. Here I've stored each of these Speasy variable objects in a list. So they're all of type Speasy variable, which is basically a very simple object with 3 main attributes and a couple of convenience functions to convert your data directly to a data frame. And in the future, we also want to support AstroPy tables. The pull request was recently closed, so it should be available in the next release of the module. So you can convert your Speasy variable object into a pandas data frame using the toDataFrame method. toDataFrame accepts optional argument datetime index equals true. It's false by default. If you put it true, it'll convert the time values into datetime objects. You can visualize quickly the data you just downloaded with the plot method of the Speasy object. This is just the plot function basically calls converts the Speasy object into a pandas data frame and then uses the pandas data frame plot function to represent the data. So the labels and the axes may not be to your standards, but it allows us to quickly visualize that the data is correct. So these are, you can see here, this would be a parameter that would be better visualized in a spectral kind of graph, and that'll be added in future versions of the program. So next, I'll go over so I was saying that Speasy variables, you can access the time data as NumPy array variables. So the time will contain a NumPy array with the time stored as seconds, Unix time, so float values. And the data is just a NumPy array with the actual parameter values. We have here the time for the first parameter we just downloaded, and the NumPy array containing the parameter values. All of the available metadata is stored in the meta dictionary. So here we've got, it'll depend on the provider you're using, but we try to include as much metadata as we can. For Amda, they're passed from space data files, if you're aware of what those are. It contains interesting information such as the dataset the parameter belongs to, the global starting and stop time of the dataset, the sampling rate, and more information, units, etc. So here I just wanted to do some plots that were a little bit cleaner. Oh, it's really much too zoomed. There we go. So yeah, Speasy is supposed to be very, very simple. You're just supposed to use the get data function, and then all of the plotting, manipulating of the data, that's on you. So that's why I defined this function to make the plot a little bit nicer, use the information in the metadata dictionary to add the correct legends or labels for each of the components of the parameter. Are there questions? Yes, there are questions. Now, if you do a request, so there's someone here that's been executed a command that returned a non-type object. So if there's no data available on the time interval you're trying to download at, you'll get a non-type object returned by the Speasy get data function. So you should check if that object is none or not before trying to use plot. If I keep going. Yeah, so here we were downloading individual parameters from Amda. Here, each of these folders represents a data set. So all of these parameters share the same times, and you can download them all at once using the dataset ID. So although it's not directly visible on Amda, you have no way of knowing what the dataset ID is on Amda's graphical interface. You can get it through the dataset ID key in the metadata dictionary. So here we can use get data with that value, and it'll return a dataset object. The dataset object is just a list. It's a list of Speasy variable objects. Sorry, it's a dictionary that's indexed by the name of each of the variables that been downloaded. So here we've got the 4 parameters that were contained in the dataset. No module name, matplotlib backend SVG. Yeah, that's, yes.
Can you zoom back in?
Huh?
Can you zoom back in?
Yes, sorry.
Thanks.
I think this is good. So you can also use it to download timetables. This is for now very specific to Amda timetables. So in your user, in the Amda's inventory tree, you can navigate down to this timetables category. So sorry, this is, I can't zoom in on this part, so you'll have to squint. And Amda provides a collection of public timetables. So they've been generated by the researchers in our lab, such as catalogs and timetables linked to various event detection, substorms, crossing of bow shocks, things like that. So in the same way, parameters are ID'd uniquely. You can get the ID of the timetable you're interested by looking at the little info box that appears when you hover the timetable you want to download. and use that identifier to download the timetable. The timetables are not cached and catalogs are not cached either. And although you can put a start and stop time, it'll just be ignored. So you'll have to download the whole timetable at once. Speasy timetable objects are basically also just lists that contain date time range objects. So they're just a collection, a container that has a start and a stop time. So this timetable contains 782 events, and the first one starts in the 2nd of February at 4:40 p.m. pretty much, and lasts only 1 second. So I don't know what this timetable is, but very short events. And catalogs are pretty much exactly the same thing. You also have a collection of shared public catalogs on Amda, and you can get the ID in the same way we did for parameters and timetables, and you'll get in return a catalog object that is also just a list that contains event objects. So they're very similar to datetime objects. They have a start time, a stop time, but an additional dictionary called meta that contains any meta information that was included in this catalog. Quickly, just going to show you how to do the download data from CDA web. So here it's MMS1 FGM survey data. It's a very short period because it can take, when the cache is not filled, it can take some time to execute. So I made sure to pre-fill the cache so that it should execute quickly. So this is how you get from the CDA web. You can also do it on SSC web. Go. And finally, for those that like to use autocomplete, you can navigate the inventory of Speasy directly. So if you go to inventory, you've got a data tree attribute, and this should contain the inventory for Amda and for SSC. It doesn't contain the inventory for CDA web yet. So let's head, for example, in Amda. And here we've got different categories depending on the type of object you want to download. So we can look at parameters, for example. There, mission. Now you've got the list of the instruments. So we can look at MFI, for example. Here we've got the data sets, IMF ACE, IMF all. And here you've got some information that was parsed from the Amda's inventory. So we've got information such as the global starting time of the data set, its stop time, a description object. For example, I'll just insert a cell above this. Oh, well, I'll just do it here then. Description, it'll give you a short description of the object. Start time, for example. Data start. We'll give you the ISO formatted start date of the data set. Similar for the stopping time. What else do you have? You have information to know if the data set is public or not, when it was last updated, it's provided provider, the sampling rate, and also the space ID. So if you're aware of what space files are, you can get very complete information about the contents of the data set by looking for this space resource. There are XML documents that contain a thorough description of the data sets. So we can look at the individual parameters. So IMF, for example, will return a parameter index object. So you can pass this object directly to the Speasy get data function. So if you're used to using autocomplete to navigate the inventory, you can just use this to download your parameter directly. So if I do Speasy get data, this guy over here, 2001, I hope there's something at this date. 01, 2001, 0102. So this should download and plot the data directly. So it can be convenient. If you'd rather navigate the inventory directly through your notebook and not have to deal with Amda's web interface, that can be a little bit jarring when you're not used to using it. There's so many products available that it can be a bit of a headache if you don't know exactly what you're looking for. You can just do it inside your notebooks. And these index objects exist for catalogs and timetables, and they're used exactly the same way. So I go, for example, in timetables, you can look at the shared timetables of Earth. As I said, I don't have any physics background, so I don't even know what I'm looking at. And the timetable objects can't really be plotted, so you can just download it directly and you'll get a timetable in response. So that's a basic overview of how you use Speasy to download data. I don't know if there are any underspace, not yet. Yes, we're actively, so Amda uses space data models to describe all of the data sets. We're actively trying to publish all of our space files, so they should be available soon. Yes. Just talk loudly. Yes, yes. Well, you mean the start and stop times for each event? Yeah, we can. So let's say your timetable is the one I just downloaded here. Yeah, the question was, once you've downloaded a timetable or catalog, how do you loop over its contents and download some corresponding data on the corresponding intervals that are contained in the timetable? So here we've downloaded a timetable that is of what size? 17 events. So if you wanted to plot, for example, parameter ID, let's set, I always use the same one. So let's say Amda's, this is ACE magnetic field data, so IMF. And now you want to download this parameter for every time interval that was available in the timetable you've just downloaded before. So we could loop this way for event in timetable, do an SPZ get data, parameter ID, and you'll have event start time, event stop time. And this should work. It's not going to print anything, so wait, stop this. There we go. So here it's going over all of the intervals that were contained in the timetable, and for each of them, it's downloading the data. We can check the time ranges of each of these objects. So temp, let's print temp time 0, or let's do it better. Just convert it directly to a data frame, date time index equals true. Temp, now the time will be stored in the index. So I want to check the first value of the index and the last value of the index this way. There we go. It went much faster the second time because everything was cached. So if you're working again and again on the same data, it's quite useful. So you can do this for timetables and you can do it with catalogs. I can also illustrate it for a catalog. So cat, let's find one first. Inventory, data tree, Amda, catalogs, shared catalogs. If you have any catalogs that you've defined on your own account in Amda, you can access it through the My Catalogs. So I've got no catalogs in my account. Shared catalogs, Earth, for example. What is this? Yeah, this one, model region plasma cluster. This is good. So this is going to be a Speasy catalog index object, Amda catalog index object. And now we can loop over it in the same way for event in cat. Just, oh, it's not iterate. Damn. That's weird. Oh, of course, sorry. So this was the ID, it was not the actual object. I have to get the data. Cat ID, there we go. Well, I'll len cat. Yeah, 27,000. It's going to take some time, so I might not loop over all of it. Let's just loop over this way. I'll just print event start time and event stop time and event meta, for example. It'll already be. There we go. I've got all of the 27,000 events that are contained. So that's a little bit much. So I'm going to delete this cell. There we go. If there are any other questions, can you say more about how data looks when loaded with a dataset ID rather than a parameter ID? Does the data share common time array, for example? Yes, it does. So if I go back here to the dataset, so insert a cell below. No, I'm sorry. So the dataset object is a Speasy dataset object. It contains one attribute, variables, which is a dictionary. You can loop over each of the items in the dataset variables. Let's see, can it autofill this? No, it cannot. Let's print the keys. These each correspond to the name of the parameter as it appears in the ACE tree. So this was stereo. corresponds to these 4 parameters over here. And each of these should normally share the same time values. So for K in dataset variables, don't need to do that. Print dataset. There. We've got the same times for all of these. Datasets, for now, we've defined datasets as a collection of parameters that strictly share the same time base. In the future, we'd like to extend that to cases where you have different time bases for different parameters. But for now, they will always share the same times. I don't know if there were any other questions. I hope that was good. Briefly, before ending this, I wanted to go over how you can retrieve your private data in Amda. So Amda allows you to define your own variables. So I could want to create a derived parameter from this electron flux data. So we can give it a name, my parameter. You can specify the time step. So if you want to have a parameter with a very regular time step data in Amda, the raw data can have very variable sampling rates. So Amda will allow you to fix the sampling rate of your desired parameter, and it'll do the job of interpolating the time and the data correctly. So I don't know, I can give it a 60-minute. And here you've got a collection of functions that you can apply to the data. Mathematical functions, statistical functions, and space physics related functions that I do not understand. This is Alvin speed. So for people that know that, we're actively adding more and more functionality to Amda. So once you've defined your parameter, you just save it in your space. There, my param's been created, and it will appear in your derived parameter directory. So then you can use Speasy to retrieve this data. So this is just the form you use, and I've already pre-defined a new parameter that's just IMF data squared. So nothing very interesting, but I just wanted to show that you can retrieve exactly the same data. So first you need to configure your account. This is done using the Speasy config submodule. It has an Amda username and Amda password attribute that can be set. So I've created a temporary account on Amda. I wasn't going to share my password and credentials with you all. So once this is set, you will be able to retrieve all of the shared, the private parameters you've created. So here's the my param that I just created. And then you can download it exactly like any other data set. For now, you have to use the get user parameter because they're not publicly available data. So we've got a different function for getting private data, and it belongs to the submodule Amda. So for each provider, we try to implement specific functions. For now, it's mostly working only with Amda. So here we're going to download this IMF data for the period specified here, and just check that we get the same thing if we download the original data and apply the same function. And we do. So that's how you do that. And that's it for me. Thanks for listening to me. question here. Happy does not have a mechanism to support password protected data and does not really intend to add that. Is there any way to get AMDA data without registering? You can get all of the public data directly in Speasy without creating an account. That's no problem. If you want to define your own private data, then you have to create an account. Otherwise, yeah, you don't need to create an account to use Speasy. If anyone else has any questions.
Any in-person questions? Not?
Yes,
Oh.
yes, go ahead.
Yes. No, I was wondering if it was possible to do the reverse. When you are logged in with your user and password in Speasy, you create a parameter and you
Upload it directly to
upload
AMDA.
at least, I don't know, the formula or whatever. I don't know how it would work to upload data from Speasy into your AMDA account.
I don't think that's in the pipelines.
Is it in the AMDA web service? Is it available on the AMDA web service?
You
If
can
it's
upload.
Not, it will not be possible. But if
You
it
can
is,
upload data directly through the web interface, but you can't do it via the web service.
yeah, not in the REST interface. Mhm.
I don't know if that'd be interesting, an interesting function. The derived parameters in AMDA are only defined by the formula you're using to, so the actual values of your private data are not stored. They're computed on the fly when you plot something. So there's no way, I mean, it wouldn't make sense to upload your parameters. We did talk for a while of a way of directly generating the derived parameters inside the Speasy API. So if I write it down, it's not implemented, but it would be nice if you could do something like this: get data, AMDA, IMF times I don't know, AMDA IMF. Or something else, more complicated functions, and just download it directly this way. These are just functions we could imagine adding in the future. It would kind of depend on if people see an actual point in having these functions. So if there aren't any other questions, I'm just going to go hide somewhere.
Thanks, Alexander.
Thank you all.
Next up is Russell with OMMBV.
So good evening, everybody. I'm back again to speak to you about a different package that I've been developing. This one's been in development for about as long as PySat. So this one's called Orthogonal Multipole Magnetic Basis Vectors, or OMMBV, or OMMBV for short. So this package is really more about solving a specific space science problem, actual solving physics, not a data problem. So most of this talk, I'm going to be focused on showing you images and motivating the science. And then if there's time, there will be a short demo at the end. That being said, the demo is up there. OMMBV is much more focused on a smaller, easier problem in a way than PySat, which is very expansive. So I don't think it requires the same kind of buildup. All right, so what is it that OMMBV is trying to solve? All right, so in space science, of course, we're typically working with plasma, right? And not just plasma, but plasma in a magnetic field. So plasma in a magnetic field can't move in the same ways as just plasma by itself. And particularly when I'm doing equatorial electrodynamics or electrodynamics in general, we need to account for that magnetic field as well as all the twists and turns that a magnetic field may take. Now, I'm sure all of you, many in here are already aware, but for some people on YouTube and things like that. Generally speaking, or if you look at the Earth kind of fuzzy, it has a generally dipole field. So it's like a bar magnet, right? So we have magnetic fields that come out of the South Pole, South geographic pole, right? And then come back and then they point back towards the Earth in the North geographic pole. If you have plasma in a magnetic field, the magnetic field itself becomes kind of like an electrical wire, electrical conductor. So if you have a potential that's applied to a magnetic field line, that potential, generally speaking, is going to be the same everywhere along a magnetic field. So this is important for equatorial atmospheric equatorial electrodynamics, because you might have a neutral wind that's applying some force at, say, a field line down here, and then that forcing is going to get mapped everywhere along that field line, consistent with the physics and distribution of the magnetic field. So we need a way to actually calculate how those things are going to translate along the field. So there's going to need 3 vectors to describe how the electric fields and ion velocities and things like that map or translate along magnetic field lines. I have a very crude sketch over here. So we got a pair of field lines. Plasma can move very easily along the field line. So we're going to call that the field line direction. But then we need 2 more vectors to account for motion perpendicular to the field line. So the main one, so the black one here is the meridional direction. So at the magnetic equator, this meridional vector is pointed vertically. If you move off the equator, though, it's going to get a poleward component, because the meridional vector is always going to point, it's going to be perpendicular to the field line and then pointing to this other one. And as you can see, just from the general shape of the field lines, it can't just stay straight up everywhere. It has to have a poleward component as you go off the equator. And to complete the system, we also need a zonal vector. So this is going to be perpendicular to the plane of the magnetic field line. So it's equivalently, it's like magnetic east. All right, the meridional is going to be magnetic up. Now, you may have heard the term meridional before in different contexts, particularly the neutral wind. And in that instance, meridional means north and south. Okay. I didn't come up with this nomenclature, but somehow the same word when applied to plasma and motion and stuff like that, the meridional vector is different than it is in neutral. So just to prevent some confusion. So what I'm trying to do with OMMBV or OMMBV is actually calculate these vectors accurately. So we can understand how forces propagate or motion propagates along magnetic field lines and understand space science, right? Electrodynamics. So I said at the beginning, the Earth's field is kind of dipolar, it's kind of like a bar magnet, and that's true if you look at the field kind of in a fuzzy way, but there's more complex components to it. It's not just a bar magnet. If you look at it on a large scale, right, there's interactions with the Earth's magnetic field with the sun. So when the sun's plasma pushes on it, it causes distortions, so it's no longer this nice pure dipole shape. Yeah, and then if we look at something like Mars, Mars doesn't have a background field like the Earth does. It might have had one in the past, but that mechanism is gone, leaving Mars with only a crustal field. So the Mars magnetic field is really is much more complicated. And if we're going to understand electrodynamics on Mars, we're going to need a vector system that we can actually apply to Mars. And similarly, if we want to understand electrodynamics on the sun, which could have maybe even a more complicated magnetic field, we need a basis vector system that's actually going to work accurately for the sun as well. So there are some existing solutions for calculating what these basis vectors are. Unfortunately, they do not actually work for these complicated magnetic fields. The current standard is originally published by Art Richmond, and it strictly only works for dipole fields and a spherical planet. And as soon as you deviate from that simplest system, the vectors are no longer orthogonal anymore, and you can't actually accurately map your forces or your electric fields or your plasma motion along the magnetic field lines correctly. Okay. So this is just a picture showing the reason why the Richmond vector doesn't or basis doesn't scale to more complicated fields is because it's based actually on the dipole field. And if you have a field that's more complicated, what happens mathematically is that dipole field gets stretched and compressed and squeezed and twisted, things like that, to try in an attempt to match the more complicated field that actually exists in reality. But when you squeeze, twist, pull, compress, all of that, you're going to distort the vectors that were originally there and correct. So I'm just showing this is a picture of a straight walkway. But with the way they did with the picture and all that, you can see that straight walkway doesn't actually look very straight. So it's just a little image metaphor. All right, so we need, or I was, so I've been trying to find a way to overcome those difficulties and come up with a system that will actually scale to more complicated magnetic fields. So I thought since there's going to be since there are students here, I might talk about a little bit about the design process as I was working on this system and on how to come up with a new system. And there was a quote that I heard when I was a young teenager from Colin Chapman, who was with Lotus Cars. So Lotus Cars is a sports car, if you aren't aware, and one of their typical features is that their cars are light even for a sports car. Okay. And their design slogan from Colin Chapman, who's like the head designer, starter was simplify, then add lightness. And the reason I kind of keyed into this quote when I was younger is that when thinking about a light car, I didn't think about adding lightness, right? I would think about if you wanted to make a car lighter, you take stuff away. And in a physical sense, that's true, but you can't just, you know, if you have a car that's sitting there and you go pull out the engine, sure, you've reduced the weight of the car quite a bit, but now it doesn't have an engine. It's not very practical. So the key is, of course, you need to be able to remove things from the car without actually impacting the performance of the car. And really, if you're trying to make a car lighter, you're trying to improve the performance. And that's not an easy thing to do, that you have to identify areas that you can actually remove material. Further, you have to figure out a way to remove the material without weakening the car and all kinds of other stuff, right? So it's it takes a lot of effort, ingenuity, and work to add lightness. So I'm trying to have the same kind of philosophy for working on numerics, but code isn't strictly speaking, you know, heavy or light. So my variant is to simplify, then add accuracy. So I need a method that's simpler than the one that's currently in use, where you distort this magnetic field and things like that to get the vectors. But not only that, it needs to be very accurate for these calculations to actually work. And my addendum to that a little bit is don't touch the data, right? So every time you touch the data, you're going to do numerical operations on it. You're going to be introducing errors. So the key, of course, is to not touch the data, but at the same time, at the end, have actually produced something that is, you know, that actually does something. And it takes a lot of specific identification and design to be able to add accuracy. You have to design specific pathways so you can move code, data, and things around with a minimal amount of impact. So after a lot of thought, I came up with a process that actually is able to overcome the challenges of the existing system. So I have just a little pictorial demonstration of how I determine these vectors. So the issue that I wanted to sort out is, so like with the ICON mission, NASA ICON mission that's currently up right now, there's instruments to measure what the neutral winds are doing. There's instruments to measure what the plasma is doing. And then we want to be able to combine, or the team wants to combine those things together to figure out what the neutral motion impact is on the plasma. So neutral winds are typically only horizontal, right? If they're vertical, then you're raising or lowering the whole entire atmosphere. So there's really not very much of that. So if you want something that's optimized for coupling with the neutral wind, you want vectors that are horizontal with respect to the ground. So what I have here is I came up with something called an apex height meter. So this is illustration. This little thing is an apex height meter. And I'm looking for a vector if that is horizontal at the magnetic equator. So the apex height, right, is the maximum height of a field line, and the magnetic equator is located at the apex height. So what I want to do is have trace along to a magnetic field line, find the apex height, and then find field lines that are horizontal with respect to that. So the way to do that is you can have a pair of meters that just reads out what the apex height is, and then you just kind of rotate until they both read the same level. And then you've got a vector that's horizontal at the magnetic equator. That's actually all there is to it. There's a whole bunch of physics that goes underneath, because you want to make sure that when you do this process, if you move along the field line and you keep doing this process, that you're consistent, that no matter where you go, you're always pointing to the same field line, and it always works at the magnetic equator. And it turns out that this process does do that. So effectively, OMMBV is spending a lot of time just to calculate what the apex heights are, and then find vectors that produce this horizontal vector at the magnetic equator. Yep. All right, so I just thought I'd show some numerical evidence of the process first before I can continue to go on. So here I've got a trio slides, a trio of plots, and I'm going to have multiple slides that follow the same format. So this slide over here is plot on the left, right? It's the longitude on the bottom, not yet. Latitude over here on the y-axis, and this is the log of the apex altitude. So this is one of the primary things I'm calculating, the apex altitude, apex height. So I just thought I'd show what that distribution is. In this case, I'm doing a test dipole. So in this case, I have a purely spherical Earth, which is not real, right? The Earth, due to its rotation, is actually bulging at the equator, but got to start simple. And then I'm going to have a pure dipole magnetic field. And unlike the Earth, which is offset from the axis of rotation, I'm going to have this dipole field aligned along the same axis of rotation. So I'm just showing that here. I'm looking at the change in apex longitude. So if I'm at a particular point on a field line, I'm going to map to the equator, and I'm going to look at what that change in longitude is. There's zero change in longitude here. You can see the scale is 1 × 10⁻13. So I'm just confirming this magnetic field is north-south. In this case, I'm also looking at what the apex altitude is, apex latitude, sorry. So the location of the apex. And in this case, you can see the scale is 1 × 10⁻6. So all this is at 0 degrees latitude. So in this case, the magnetic equator and the geographic equator are aligned. And then I run my whole process. I calculate all these vectors. And there's actually two ways, the two pairs of vectors are going to come out of this process. And it turns out if you go through the math, those vectors will only be the same if my underlying physics and things like that are correct. So I do these two calculations, and then I compare the difference, normalize, and to 6 digits of significance or so, I get the same number. So what I'm showing right here is to high precision, my basis vectors are physically correct and are accurate for electrodynamics for a purely dipole field in a spherical Earth. Now, the current system from Richmond, as in the ApexPy package, will also produce orthogonal vectors for this one situation, spherical Earth and then a pure dipole field. But as soon as you move from a spherical Earth to a geodetic Earth with ApexPy, all those vectors are no longer orthogonal and the system starts to break down. But there hasn't actually been a change in the magnetic field. So there really shouldn't be a change in the vectors. It's just an aspect of the ApexPy process. So I'm going to move to a dipole field with a geodetic Earth. You can see these plots are effectively the same. The colors are different. I'm just doing different color maps. Do the performance, and my vectors are just as good with the geodetic Earth as they are with the spherical Earth. So this is significant because this is the first vector basis system that's actually been able to do this. So you can still do accurate electrodynamics with this system, but there are more complicated fields than that. So what about higher order moments? So here's evidence for, I've added a quadrupole magnetic field. So I added a pair of dipoles also along that same rotation axis. And the strength is big enough that you can see here that the magnetic equator is actually no longer at the geographic equator. I've pushed it south. So the magnetic equator is now a few degrees, 5 degrees south. Apex altitude, you can see, is also shifted. And there's no change in apex longitude because it's still just aligned along Z. And again, the performance here is to 6 significant figures or so that my basis is orthogonal and correct. My both 2 pairs of calculations come out with the exact same number. So this is a significant field. It's got a multipole component, and I can still do completely accurate electrodynamics. So I'm very proud of this. All right. And even more complicated, I can add up questions.
Yeah, from the chat. Why is there a band of higher errors near the poles with apex lat spherical Earth?
This one? No, that's geodetic. Why is there a band of higher error?
Yes, that was the question.
Oh, so the scale here is there's such a small variation in the numbers. When I do the plot, the variation is at 1 × 10⁻⁶. So it's the tiniest change in latitude. Thanks for the question. I did this one, yeah. Then I did another case. What if instead of all the dipoles and stuff being aligned along the rotation axis, what if I put the dipoles, a quadrupole, a pair of dipoles, pointing along the Earth-centered, Earth-fixed X direction. So that's along the equator pointing to 0 degrees longitude. So now you can see the field distribution is getting more complicated. So instead of the apex altitude being just like this kind of nice horizontal lines, we start to get a little bit of a Charlie Brown equator, right? It goes like this. And you can see the same thing here with the apex latitude, in that the magnetic equator goes between north of the geographic equator and then south and then north and then south. And similarly, you can see with the change in apex longitude, now there's going to be a varying, instead of the fields being north and south, right, they're going to pick up east and westward components to go along with that. So this is, again, much more complicated field than the previous ones. If I do my same process, I get, again, the same accuracy. So my accuracy really hasn't changed at all in these plots. If you look up here at the 6 in the location, it's remaining essentially fixed for all these plots. And you can see in this one a little bit better exactly where the magnetic equator is. It's this little band of slightly better performance, right? But maybe somebody would come along and say, yeah, that's not really all that distorted. Your magnetic equator is only going, what, plus or minus a few degrees. So I added another pair of dipoles to make a normalized quadrupole. So now there's a pair of dipoles like this, a pair of dipoles like this, and then we still have that original dipole moment. So it's even more of a Charlie Brown, right? So it's the same kind of pattern, but it's even more extended. Similarly, the change in latitude, right, a few degrees. Change in the apex longitude. I do my accuracy plot again, and I get the same thing. So I'm maintaining the same performance for all these components. So then I went to IGRF, right, the International Geomagnetic Reference Field. So it's, for those who may not be familiar, IGRF is an international collaboration that involves years and years of measurements, magnetic field measurements from a variety of missions, spacecraft and probably ground-based. And then there's a team that collects all those measurements together to do a best fit magnetic field for the Earth as a function of time. So this is for, I think, modern times. So the magnetic equator now you can see is the classic is the Earth's magnetic equator, but it starts out about 10 degrees. It jaunts down to about minus 10 degrees before going back up again. So this is even more distorted. I mean, even more non-dipolar than my previous test fields. Similarly, you can see the change in apex latitude from a little less than minus 10, more than minus 10 to 10. And similarly, the change in apex longitude, just to confirm that this field is looking right. And now if I do look at my accuracy, it actually does a little better. You can see that minus 6 moved to the right some. Now the distribution of error changed slightly. Now I've got these lines of very low error, and then otherwise it's kind of smooth around that minus 6 number. But anyway, the performance in an absolute sense, even if the distribution is a little different, is the same level. It's actually a little better. So I did all these at the same scale size, but it turns out IGRF will continue to do better. If I keep changing the scale size, I can actually do better than this performance. So I'm going to just show some images now. So this is like the scientific proof. And I gave a little story about the development, but most of the time when I was developing OMMBV, I was looking at a whole huge series of unit test plots, literally hundreds, looking at all the different components of OMMBV because there's a variety of tools that all have to go together and they all have to be high performance and about the same level of high performance, right, for the accuracy to be maintained for all different situations and all different magnetic fields. So I produced so many plots. And then when I started looking at these in high resolutions, I was literally shocked by what came out because I have never, at least in my experience, seen unit test plots that kind of look like this. Oh, sorry, I got a little ahead of myself. So I have a comparison here between my OMMBV vectors and the apex pi vectors. So this is at the magnetic equator, and I said my goal was to have vectors, zonal vectors that were horizontal at the magnetic equator. So check out this solid blue line here. So that's the zonal. This is U for upward. And you can see it's right at 0 all the way across. The apex pi vectors and the dash are not the same. You can see they have these distortions. And then similarly for the northward, we're actually kind of close. And then I've got the eastward component up here. So the zonal vector is magnetic east and it stays, it's points east most of the time. This plot over here is at 35 degrees magnetic latitude north. Same comparison, but now you can see there's more structure in mine, but there's much bigger differences between my vectors and ApexPy than before. And in some areas, my vectors actually have the opposite sign. So this is really significant because if people have been doing analysis with ApexPy vectors, they're going to be pulling out the wrong sign. Those vectors are not orthogonal. So they're not going to be pointing along the right directions. That's just how it's going to go. So there's a lot of physics here that for all these models and analyses that have been generated with ApexPy should really be switching over to OMM because mine is physically accurate and maintains orthogonality. And it's going to have an impact on the outputs that come out because the directions in ApexPy are not actually correct. And then just to note, you can see my zonal vector, the red one up here, pretty much maintains the same form, even at the higher latitude. But the ApexPy one is not, it changes its shape. All right. A lot of what I do is actually field line tracing. So I spent a lot of time making sure all parts of this field line tracing are accurate. So after I had done a bunch of stuff, then I wanted to get a data set to validate against. And a number of people, and has been discussed in this conference here, been using the Cycon Echo field line tracing, and that's also offered by OmniWeb. And while I could run it locally, I thought it would be good for this type of comparison to go to NASA's OmniWeb, where it's configured by somebody else, and I just tell them, hey, run this field line tracing stuff for me, tell me where the foot points are, and it sends me back a list. And then I did the same tracing myself to get the same foot point things. So by foot point, I mean like the magnetic field line around 120 kilometers near the bottom of the ionosphere where conductivities and things like that are high. In most places, our field line tracing is the same, but you can see in these two longitude sectors here, there's actually a difference of multiple degrees between the foot points from the Cycon Echo and from my model. And I've done a ton of testing on this tracing, and the uncertainty of my locations for these foot points are many orders of magnitude less than degrees. Just a heads up, if you're doing, at least for equatorial type applications, I would say OMMBV is going to be more accurate for determining field line properties. I haven't done a complete analysis across all things. Okay, so hopefully I know I've shown some results and some of those things. And now I'm going to go actually show some of those unit test plots that I was talking about, because this is, I'm proud of the science, but then this stuff came out and I found it was pretty shocking. It's always tough on display versus a screen. So I'm not sure it's going to give out quite the detail, but this picture here, this is the accuracy of my OMM vectors. So I showed this plot before. This one, where the step size was the same as the test fields, but I noted, hey, this is not the minimum in error I've been able to find. So I actually kept going to smaller step sizes and the errors continued to decrease by at least an order of magnitude. And then I get this type of picture. So this is longitude on the bottom, it's latitude on the top. And I'm not actually showing the, I don't put a color bar on there. I didn't put the axes on there. I didn't put the title on there, because when this image popped out, it didn't look so much scientific to me, even though that's exactly what it was. It looked more like art, frankly. And then I found if you take off the axes and you take off the color bar and you don't put a title on it, and then you show it to people, that's pretty much more how they interpret it, right? Because you don't get the actual technical information. All you have is the relative variations in the data. So to make this, I just plotted the data, and then I used matplotlib's color maps that are perceptually uniform. And then I just said, hey, here's the data, plot it, here's the color bar, here's the color map, and then I just let it do its thing. So all the colors that are coming out here are just coming straight from the data. I didn't tweak it, I didn't turn it, I didn't twist it, I didn't do anything on the visual sense. All my effort was spent on the technical side, coming up with the best algorithms, the most robust things, all of that. And then when I plotted it at high resolution, this is what popped out. So you're not getting the full thing right here, because I've actually calculated these at 8K resolution, as in like TV or a future TV 8K, so double 4K. And I don't think this projector is doing 8K. That's probably not even 4K. But anyway, so super high resolution, and it looked, I'm getting excited and getting ahead of myself. when you look at some of this, it almost looks like it's painted. Somebody comes along with a paintbrush and is putting a color here and putting a color here, and it's all smooth. When I was growing up in Austin, there's a street there that's kind of famous for music and having fun downtown. It's called 6th Street, and on the weekends it gets shut down, so there's no traffic. And for multiple blocks on both sides, it's just like club and bar and music venue over and over and over again. And there'd be some people, some artists that would be working on the streets, right? Because there's a lot of people there. And they would be doing stuff with spray paint on stuff, and they'd take newspaper and they'd be messing around with the paint and smearing and smudging and doing kind of stuff like that. And these kind of details that are coming out here kind of remind me of some of those things that those artists on 6th Street were doing. But I didn't have spray paint, I didn't have newspaper, I wasn't doing any of that. This is just the image that results. Now, it might be considered maybe just technical because, again, I'm doing physics, right? And supposedly in physics, there's right answers and wrong answers. So this answer is right, but this image isn't like objectively specified ahead of time. This image is at like significant figures of 7 and higher. So we're talking about really small details and a whole bunch of different processes that I've put together. So it kind of reflects me in a sense, because I spent a ton of time in building an accuracy and robustness and all these things for all these different processes. So it reflects my technical sense in a way, but it comes out very artistic, which is kind of how I view myself. So I think that's just kind of nice. So just as a little bit of a reference, here in Madrid, I think we're right about there. So-and-so. So this is actually from -50 degrees to +50 degrees latitude and then all the way across. So I think that's about where we are. All right, so this is the accuracy of OMMBV applied to IGRF at the default scale size for OMMBV. So this is perhaps not the absolute lowest error, but it's in that range, right? It takes significant computation time to do this at 8K. This here is, so I told you before, my goal was to get zonal vectors that were horizontal, right? So this is how horizontal are my vectors? This is zonal apex gradient, and it should be 0. And it looks like 0. And you probably can't see it from the audience, but it's not perfectly 0. And there's actually some variations. I can't even see it. Around here. Oh, yeah, right here. And up there. So to help you actually see what those things look like, I thought I'd zoom in super well. So there are areas where I get some kind of random distributions like you would expect from a unit test plot, randomized errors in a way. But even on the super zoomed in, once you get out of these little areas, it's pretty well flat. So I think some of this is kind of interesting because normally a question in science like, how does the magnetic field make you feel? Doesn't really make any sense. But this here actually is a direct aspect of our magnetic field and its physics. And it could generate a feeling. Alternately, how does 0 make you feel? I mean, imagine you painted a room with this. Do you think it'd have an emotional impact? I think it would. Good, bad, maybe.
Russell, question.
Yes.
Have you tried parallelization to accelerate the code?
I do run it parallelized. So I got a pretty hefty machine at home, a Mac Pro with 16 processors with hyperthreading and 192 gigs of RAM. And I maxed that out for a long time to actually generate all these. So, yeah. So this is another aspect of the code. It also looks pretty artistic to me. It doesn't come out super well because there's a lot of black, but I pointed out an error before where there was some of that random stuff. So this plot is actually the tolerance of the zonal vectors I go through. So there's an iterative process, right? So I generate a set of vectors, do some operations to figure out how good they are. I generate a rotation angle I need to go through to get a better vector. And then I track the change in the vector loop to loop, right? So I specify a tolerance that has to get down to, and that's what this plot is. It's the change in the vector with respect to each loop. And those areas where that apex gradient wasn't quite 0 are here. It's this stuff. And if I knew what that was, I would work to get rid of it. So if anybody has any ideas on where these structures are coming from, I would love to hear. But I think I'm maybe near, as good as it's going to get, because that distribution, you can see there's some along with the magnetic equator there, that shape is in there, but there's nothing that really super stands out to me. So these are kind of the results. These are still the end. This isn't so much what I was working with, but it was something I was monitoring the performance. And I was just really, truly surprised by how they ended up. So I mentioned before that the Earth is not actually spherical, right? It's a geode. But the previous vector systems didn't support that. So I built to work with geodetic stuff. So I had to have conversions, right? From Earth-centered, Earth-fixed, or other coordinate systems to geodetic and back. So I wanted to verify my performance of those things. And this is actually the performance I have between ECF and geodetic. The black areas here are where there's actually no error. So I just did a fill for black. And then all this gold and stuff that, again, that's coming in, it's the color map from Matplotlib doing its thing, perceptually uniform. If any of you have taken numerics course before, you may have heard that a single subtraction can ruin all your precision. And if you haven't heard that, then you should really look at that up. But seriously, if you have two numbers that have very different magnitudes and you subtract them, you can destroy all of your precision in that single subtraction. So we've got this bar thing here in the middle. What's that about? And I didn't get it at first because I was actually doing this for a long time. I do it at low latitudes, just plus or minus 20 or so. So I didn't have to do as many locations for, keep things a little bit in time. So I didn't pick it up. But here I think there's one part of my code that does longitudes from minus 180 to 180, and another one that does it from 0 to 360. So there's a shift. I have to add 360 to some of those. That's what this is. So this is the loss of precision from shifting from from being minus 180 to 180 to 0 to 360. That's from an addition. So now all of these uncertainties are actually at the scale of 1 times 10 to the minus 13. So it's not big. I didn't pay it that much attention, but I just found it as a pretty interesting addition to this plot. So all these circles and stuff that are coming in, of course, I'm not specifying them. This is just the transformation from ECF to geodetic and back. So I suppose in a sense, I shouldn't be surprised that there's circles and stuff involved because that's, this trig. But this one is along the Y direction. Similarly, I've got one along the X. I applied a different color map here, and it just, again, I just found that it produces pretty interesting patterns. So. Moving on, here's another one. I don't know how well it comes out, but you can get a sense of shading of all these different circles overlapping in the middle. There's reduced error right along the right along the geographic equator, magnetic equator. I did take some art when I was in high school, and in that class, you start out by drawing lines for stuff, and then they quickly have you move on. If you're going to draw something, you don't draw a line, you shade, right? So, and that's what it looks like the universe is doing. So this is that circle is coming in over here. It's not strictly a line across, it's just different densities of the air. This line. And I've actually looked at even higher zooms here, and it's not very repetitive at all. Everything, even it's just dots or no dots. But it's a complicated distribution, so I think it makes it very, more visually interesting. And even if you're looking at a lot of it, you may not know that. I think it still ends up coming across. This is the uncertainty in the apex altitude. I don't know how well all these different variations of purple are coming across. But look at all these things. I've just really had never seen unit test plots that kind of look like this, even remotely. And even then, I mean, again, I've applied a full color map to this. I didn't restrict it to the purples. I applied the same Inferno, or I think this one's Inferno, maybe Magma, like the other ones, but it's just the distribution of the data that I guess that the highs and the lows are far enough away and the density is low enough that what you end up with is basically this study of purple. So this one is at mid latitudes. What if we zoom in so we get low latitudes? This is a different color map, but it's the same type of thing. Again, we still have the same structures, And I don't know how well you can see it, but then there's all these little distortions that are showing up. It takes a while because this is a big image. There's a lot more over here. It's a little surprising because so much of it is smooth, but then we get these little swirls and whatnot. So I thought I'd just zoom in on one of those. I don't think this is what it is, but if there was a plot the other day of reconnection for magnetic fields, right? This is like that same type of distribution. It's not reconstruction. We don't have multiple magnetic fields. And I actually don't know what these things are, but you got these swirls and these distortions over here. To me, it kind of looks like an optical phenomenon, like a lens that's not ground quite right or something. So I don't know what these are. Maybe I'm hoping somebody in the audience might. My current suspicion, it might be an aspect of looking at things with a fixed step size. So I'm kind of curious if these types of things have already been identified or not and what they are. That's not really, super on the physics, but if you find something that other people haven't named or not, then that's an opportunity for, perhaps to make some more advances. It's the same type of thing. This is a different aspect of the apex altitude. And in this case, wherever there's no error, I actually backfill with white. And color perception for humans is not really a linear thing. So if you start adding white in there with different densities and stuff, but it can actually push the colors in the different directions, I think. So even though this is the perceptually uniform colors for matplotlib, if you go and look at that color bar and you look at this, I'm not sure you're going to necessarily see every one of these colors in that color bar, even though I didn't explicitly add or redefine any of those. And then if I do the same type of thing all the way up to high latitudes, you get this structure. It almost starts to look like a flower. Right? You get that distortion because we're down here at minus 90 degrees. But you keep getting these patterns of overlapping petals and things like that. And I just, even after seeing the other ones, right, I have to do a whole long run for each of these ranges. And the high latitudes I did the last, when all this kind of flower stuff popped out, I was surprised again. And we still have like these distortions, these lines, almost like a fingerprint. I don't know. Hopefully one day I'll sort out what those are, or somebody will tell me. So this one's not just more color, so it's a different color map. This one I'm looking at an uncertainty in the apex location with longitude. And the procedure that I do is you go to a place, you have a field line, you get your apex meters out. So it's measuring stuff at the magnetic equator, and that's how you figure out the vector, is based on the mapping of your location to the magnetic equator. So these lines here are very low uncertainty lines. And if I was showing you the one that was all the way to high latitudes, you would see that these actually go to the magnetic poles. So that kind of makes sense in a way because everything's mapped along a field line. So if you're on a field line that for whatever reason is low uncertainty, that property should be maintained everywhere along the field line. And that's true with these. But then you get to this circle. And then you got to wonder, what is this circle about? Because everything was about mapping to the magnetic equator. So it's not about local properties at all. But that one's not, I mean, it's a circle almost around the magnetic equator. So I have no idea what this is from. Of course, these are unit test plots, right? These are my uncertainties. So in a sense, everything on there is supposed to be something I don't understand, because if I understood it, I should be able to fix it, right? So now this one, I mean, it's not so much a problem. These are low uncertainties, so that's good. But I really don't understand what that circle is about. It's somehow reflecting local properties in a way for a method that doesn't depend on local properties. So I just thought I'd point that out because it's always kind of interesting to me when there's things that don't make sense. So this isn't uncertainty anymore. I just plotting the actual unit vector. So this is the zonal unit vector, one of the components. I think this one's up. I put it in my notes, but I can't see the notes because I'm on Zoom. I don't know. I just thought it was pretty. And then I've got this one. It's also an aspect about the zonal unit vector, but certainly with today's kind of political situation in the world, this science plot, which is technically just a science plot, could almost have some political significance to it, right? Maybe. I don't know. I think if I printed that out and maybe put that up, held that up in Russia, I'd probably get arrested. So I just never really thought so much about the political statement of a science plot, but there we go. All right. So my conclusions: OMMBV works. I know I didn't do all the color bars and stuff there for you, but OMMBV works to very high precision. So it's taken me 12 years. I was directed as my first job as a postdoc was to come up with these vectors, and I finished it. OMMBV 1.0 was released on December 24th, so it took me a long 2021. That's the right one. Yeah, so not very long ago. So it took me 12 years. It wasn't 12 years continuous, of course, but it did take me 12 years to actually figure out that simplification. I had a variety of solutions before that were all wrong, which is how it goes, but I just kept with it. And then once I figured out how I finally got the right system, it took me several months to actually go through and build a high accuracy and high precision path throughout the code so that all the different systems would work together and nothing would get sorted out. So that's my add accuracy thing, like add lightness. Accuracy is something that it requires extra work to do. So the science software is freely available. It's up on GitHub, R Stoneback OMMBV. I'm also trying, is there a question? Oh, no. So I also recently started my own business, and I still plan to continue doing science. But since I'm not at a subsidized institution, I kind of have to come up with my own alternative kind of background funding. So I'm trying to, I'm putting this printed art now up, available for purchase. So I don't print, but I'm uploading my art to a print-on-demand service that will ship worldwide, actually. So if any of these things are interest to you or somebody that you know, you can go to that website, russellstoneback.pixels or whatever, and you can buy it in a variety of sizes if you're interested. I'm also trying to some NFT things because I don't know if you all are aware about non-fungible tokens. But one of the classic challenges with art is what if somebody comes along and says, I've got this masterpiece painted by so-and-so way back in the day, I want to sell it to you for millions of dollars or something like that. The first question a prospective buyer is going to have, is that the actual piece of art from the artist? How do I know that that's the real thing? What's the provenance? And in art, there's usually a lot of problems with provenance. If you check out on Netflix, there's a whole bunch of documentaries about where that whole process has gone awry. But with NFTs, it actually provides provenance. That's the main thing that you get with that system. And there's a bunch of people out there that collect things. So they'll collect football cards, baseball cards, all kinds of other stuff. So those results I was showing before, these things, making them science trading cards. So I'm going to see if perhaps there's any interest in that. So I'm going to put those up as NFTs as well, just to, why not? So maybe we can, politically, there's a whole group of people now that are anti-science. And we can go out there and we can, yell at them some more about science does this, science does that. But we've been doing that for years, and that hasn't really made too much impact. So it's not so much an intellectual path that we need to go, but perhaps an emotional one, get people attached emotionally somehow to science. And for a whole group of people, if they're emotionally attached to something, they're going to be much more receptive to whatever content people say, or just assume it's correct. So I'm just going to be trying to do some of this stuff in the wider world and see what happens, a bit of an experiment. Yeah, see what kind of emotional connections I can get with people with this particular purple or all this blue. And for each of these, I'm actually doing all the matplotlib perceptually uniform color maps. So for each image, there's actually 10 versions. I do the color map as it is, and then I also do the reverse. So I think that can be kind of interesting for art. Not everybody sees colors the same way. So if people are looking at paintings, they don't get the same reactions to them. And it might be interesting to have things where everybody pretty much has about the same experience. Okay. Well, I think that's it. Oh, I got a few minutes for the demo, so I can show that to you. Okay. Assuming it's still loaded up. Okay, so I only have the one demo, unlike PySat, which had, a ton. And I'm not showing everything here. I'm just going to do a simple plot. So I've taken this from a plot that was one of my unit test plots. It was not one of the fancier art ones. It was a bunch of field line traces with the vectors on it, just so I can make sure globally things were doing the things that I was expecting it to do. I have additional mathematical checks in the unit test, but hey, I already produced so many plots. What was wrong with one more? Now I say a version because it would take too long in this demo to do the same density of vectors and things that I did before. But the code is here, so and I'll show you. You can update it if you want to see it on your local system a little bit better. So starting out community packages, right? Import. The well-established packages first, then local packages. I'm just going to define some latitudes, longitudes, and altitudes. Going to define that. Going to make a figure. Going to be 3D projection. So going through this subplot thing, I'm going to define a date, January 1st, 2000. So most of prefers to work in ECEF. I know people don't like to work in ECEF because that's not as natural. It's more like, longitude, latitude, and all that. So the typical workflow is that users can provide locations like that, and then we need to convert that over to ECF. So in this case, I'm assuming the user provided geocentric values, convert that to ECF. Then I'm just going to iterate over all those values. For each value, I keep getting caught. For each value, I'm going to do field line trace through that point to get a full field line all the way to both to northern and southern foot points. So that's this. Full field line trace. This is my starting location. This is the date. This is the altitude I want to go to. Now, normally for foot points, I do 120 kilometers because of physics reasons. For performance reasons for this demo, I just made it a higher altitude so it doesn't have to trace as much because it's just a visual field trace and it doesn't matter. After that, I'm going to take, I'm going to down select on the trace so there's not as many points. And then for each of those remaining points, I'm going to calculate the vectors and then I'm going to plot them. So I have just a couple print statements here, tracing field print statement and a calculating basis statement. It's just to show the relative performance of these things. The trace field is really fast. The basis determination is slower because it requires many tracing field operations to get high accuracy. It's just how it goes. I ran this while sitting in the audience during the last one, so you didn't have to wait for it to complete. But then this is what we get. So it's kind of hard to see the vectors because the density is low. Sorry about that, but it's just a timing thing. If you want to increase the density, you're willing to wait for the heloclad to run it, that's fine. Then you can just come up here and where is it? This thing. Instead of stepping through every 18th element, reduce 18 to something lower. Maybe even 1, then you retain all the points, whatever it is. So, it's going to require more calculations, but that's just how many points it's going to do the vectors. So I'll trace along this one. This is a field line. All the way down to there. There's the southern foot point. Here's the northern foot point. The green arrows here, this is a zonal vector. And then it gets a little confusing down here because just of the tracing of the field line, some of the vectors start going over each other. They are correct. The meridional is always supposed to be perpendicular to the magnetic field and vertical at the equator. So this is that red one. You can't really see him here, which is good because that means it's perpendicular to the field and it's pointing out. But you can see it gets, no, I don't know what I clicked. The offward components. And then there's also the field aligned vectors in purple, which you really can't see, but that one's there, that one's there, that one's there. So correctly, it's right along the field line. There's some other things you can do with OMMBV. You can get the apex location info, which is one of the biggest things. So we've got this function, you put in the position that you're at, it gives you the apex location. So this is one of the things that I keep doing over and over again, right? This is the apex meter that I had in my simple balance with the meters on it, all right? And this thing actually goes through and it calculates a bunch of different field line tracing. So you can pick like the normal step size along it. To make sure I get the most accurate apex location when I do a trace, I actually then do a binary search around the, well, I say binary search around that apex location. So I try to get the most accurate one. That being said, if you look at IGRF at high resolution, it's not like this smooth line, it's jagged. So I couldn't do strictly binary search because then I would actually lose the absolute maximum. So it's a binary search pattern, but there's more steps. So right now it's defaults to IGRF. So it's good for the Earth. That's where my focus has been. But as I was talking about at the beginning, I would very much like to apply this to other magnetic fields that previously had no vector basis whatsoever, like the Mars crustal field and to the solar magnetic field. So there's actually hooks that are present that you can, users can put in their own magnetic field function and their own step function to move along that magnetic field to do the tracing. The ones I have are all written in Fortran and things like that, but there's links at the top where you can write equivalent ones and hook them in, and then this process should work for those other fields as well. So like I said, I only released this 1.0 late December, and I'm working on the manuscript, hoping to be submitting that in the next few months or so. And then, looking for funding and perhaps collaborators to take this same process to the sun and Mars and of course other planets too, but the other planets like Jupiter and Saturn and all that, their fields are much more dipole even than the Earth. So while it would work there and it's good to have the best accuracy, I'm trying to move to the more complicated fields that were previously completely inaccessible. And I believe in one of these talks, or maybe as a PyHC spring meeting, there's a package PSI, PY, SciPy, a different SciPy. And that one does have like the magnetic field, 3D field for the sun. So that's kind of my current thinking is hopefully I can connect with that group or at least the software and hopefully connect it into here. So I think there's only a few minutes left. So open to questions. If there are any, and if not, anything on Slack?
Can you suggest how to plot the geomagnetic equator over a map, either using your method or any other method?
Oh, sure. Well, if you want the geomagnetic equator, then you want this apex location info. So you put in a starting location, and then it'll give you what the apex or the geomagnetic equator is for that. So you can just apply this thing as many times as you want until you get your plot. So it should be pretty straightforward. So I have some coordinate transforms in there, just to notably, what I didn't know at the beginning of this process is that one way to geodetic coordinates is easy, but going back is a lot harder, and there's a number of iterative methods out there. But those ended up being a little too slow, and searching around the internet, I found some paper from somebody published from the Navy that had a closed form solution for that backwards transformation, which I'm using. And the accuracy and stuff looks good. When I went to go find it again, though, I couldn't. So I've unfortunately lost the reference, but I do still have the math. So that's the good thing. So just anybody's out there working with geodetic or something like that, you might want to consider this transformation over some of the more common iterative methods. There's a variety of tracing things, and at the top level, OMMBV is pretty simple because it's all focused on the basis. I have a few of these methods that used to be at the top level. They're now deprecated. So if you run them, it'll be like, this is the deprecated version, but the next release, they'll be gone. And in the future one, you're only going to have like these two things at the top level. This is the original one, which has all the options and stuff exposed. But the defaults I have for the Earth, even though there's a huge range in apex field line lengths, right, as you go from the equator all the way up to the pole, the default should work pretty well for across all of them. So the ones for users should probably be doing is just this calculate geomagnetic basis. It just ends up calling this thing internally and then putting the outputs up into a nice form and then returning those. Okay. Well, that's it for me. Thank you very much.
Thanks, Russell. All right, we're at our next short break, so see you all in 10 to 15 minutes.
Oh, thank you. Oh, I'm going again. I am going again right after. All right. Oh, yeah. Oh, thanks. That is the plan. Oh, yeah. Awesome, thank you. Oh, yeah, it's better. Oh, yeah. Yeah, of course, personal favorites, right. Oh. Yeah. Once I saw this, I started looking. Oh. Oh, yeah. Right. Mhm. I got it. But I didn't know that. Yeah, I know. Wasn't trying to do that. I mentioned the Shawnee. Yeah. Like, yeah, well, I did. Let me go step up. Anybody in the audience happen to know how to do full screen in Google Docs? I'm logged in, but it's not in English and I can't understand it. I'd share the screen, but I can't quite do that yet.
All right. Let's go ahead and get started with our final session of the summer school. Going to be doing a Python learning session. Russell will go first, then John Niehoff will be on virtually, talking about configuring and using PyHC packages locally and so forth, and then some info on Python testing and so forth. So take it away, Russell.
Thank you. All right, good evening, everybody. This is going to be the last time I'm talking to you, though that's probably because the conference is almost over. Officially speaking, though, this presentation is not mine. I did not come up with it. This is Sean Polson's work. He's one of the organizers. He was originally sitting back with Julie, but he had to leave the conference early for some family happy stuff, so he couldn't be here today. So I volunteered just to fill in. So just pretend I'm Sean. All right, so when we were organizing this conference, we made the decision early on to not teach Python, right? And the reason being is that there's already a lot of resources out there on how to use NumPy and SciPy, Matplotlib, things like that from NumFocus and other groups. And us trying to recreate that without as much experience probably wouldn't do it as well. So at the same time, though, we had set up Helio Cloud so people didn't have to be responsible for their own Python installations and things like that. And we are hoping that there are some new Python users, and we did want to give you some information. Hopefully you're excited about the packages that we've demonstrated today. So when you go home, we just wanted to give you some information how to get Python working there. So that's kind of what this is going to be talking about, just a quick overview of Python basics, and then how to install the variety of ways you can install Python on your system and get going locally, with science and all that other good stuff. As you can see, the language changed on me just because I think I'm in ESA, and I don't see a button to change the language, and I don't see the button for full screen. So I'm just going to go through like this unless somebody, can you tell me?
Wait, but if you do the one that says V at the top, V's thing, like the third from the left. Yeah, click that and then the first button there.
All right. Good to have an international audience then. Thank you. All right, good, the buttons work too. So yeah, Python basics, as I said, this is mainly focused on, just quick overview and then giving you the tools to set it up if that's something that you need. So in this talk from Sean, what is Python? How to install Python, different ways to do that. And virtual environment. So there's your system probably already has Python and things like that. You don't want to mess with it. So there's ways to have multiple Python installations. One of those ways is Anaconda. We're going to talk about installing Python packages and in particular PyHC stuff, and as well as how to choose a Python platform. All right, so to begin, what is Python? So Python is free, open source, high level, interpreted, dynamically typed, object-oriented language. That is, of course, a bit of a mouthful. So open source, right? There's a community of developers behind the code base. While it's not necessarily free for those developers to develop that code, those developers are willing to put the results of their development, the actual code, on the internet, freely available for anyone to use. There are different licenses, right? So the developers can choose under the terms at which they release that software, but with open source, there's not a charge. For healthy communities in open source, anybody can contribute. That's going to be especially true in PyHC, right? And they help decide the future of the language. So there are definitely people that like Guido van Russen, who started Python, so he probably does have a good say, but he's not in control. There's whole groups of people with Python, because Python is in and of itself is not just some monolithic thing. The core package for Python is a variety of packages that were developed by different people for different reasons and things like that. So it's not controllable by any one particular person. Okay? And if you have a large user base within your field, right? You have a large user base within your field, you can establish a variety of packages, make things more useful. And then once you start getting some packages, it makes it easier to do stuff, and that tends to beget even more packages. Right? So open source is actually a pretty significant development, I think, kind of for humanity, and rather than all the code being locked up with corporations, it can be out there in the world for everybody to continue to build on. And since the actual source code is available, all those ideas and stuff don't get taken away. They can continue to be built upon and help us, you know, improve humanity through the future. High level. So Python is optimized for developer time. It is not optimized for computer time. Okay? So it's supposed to be easy for users to work with. It's supposed to be a little bit more natural language and things like that. So it takes less code / less effort to get real work done. As always, like there's always an XKCD comic for that, right? So I didn't want to add anything to this and mess with Sean's talk. But if any of you are familiar with XKCDs, right? So like kind of like stick drawings, the artist is actually a physicist. They're pretty funny. You can go to xkcd.com, but he's got one Python comic, which is an experience kind of that I had when I first learned Python. Python almost seems magic, right? Python itself does all this stuff, but then there's so many packages out there that whatever you want to do, there's a good chance there's already a package there to do it. So the title of the comic, I mean, the comic itself is somebody just does import anti-gravity and then they fly off the earth, right? So Python and all these different packages make it easy to do stuff because other people have already kind of done the work. And it can almost really, it can seem magical for years. It's really good. So low-level aspects of the machine are obscured. So you don't really have to worry about memory access or all kinds of other things. You can just focus on the work that you want to do. And then later, if you need some more features, there's probably a package to make that done possible. Like with my OMMBV package, I didn't specifically parallelize it, but there are packages out there for Python that make it possible. And then I can just distribute a bunch of different, serial tasks across a variety of processors. Commonly used functions, data structures, utilities are already baked in. So just Python itself is already pretty complete. So that's good. It's also the third-party packages and things like that are also expanding. So there's a lot of stuff that's already complete and you can just use that rather than roll your own. So it'll save you a lot of time. And then the people that have invested time in those packages, have spent time to make sure that software runs well and all that. So it's nice. I used to work in IDL, interactive data language. IDL is pretty widespread in space science, but the user base for Python is not just scientists, and it's not something like even just space science. There are probably millions of developers out there for Python. So the user base for Python is just orders of magnitude bigger than any of the science software that we would have been using historically. And the more people you have working on it, the more ideas you have, the more code that gets written, the more supporting packages there are. And also, if you want to take science results like from IDL and try to give it to the wider public, they're not going to have IDL. They're not going to have any of that support. But with Python, because there are so many people that are already using it, we can actually take our science software and rather than just keep it to ourselves, we can contribute back to the open source community. And hopefully we can form more connections. If we have, say, millions of Python developers, out there using science software and they have good experience, do you think their view of scientists is going to improve or get worse? I think it will get better. Python is interpreted, right? So like unlike Fortran, you don't specifically compile it ahead of time. You just write your code in the Python English and then run it. There are some technical details under there, but again, with Python, it doesn't really matter at the user level. Who cares, right? And because it's not compiled, it's portable to any machine without modifying the code, in principle. Sometimes there are little differences with Windows and things like that, but most of those I think have been smoothed out. Python is sometimes slower and more memory intensive than compiled languages. That's okay. Developer time is expensive. People are more expensive than computers. Even a really highly spec machine from Apple, you might spend say 15 grand. That's pretty small compared to a developer salary for a year. That machine can do, a ton. Who cares if you have to buy more RAM? It's comparatively cheap. So I think developer time is better to optimize for than computer time. Unsurprisingly, I'm big on Python. It's dynamically typed, so if you define a variable, you don't have to say it's an integer or a float or a string. You just say, here's a variable, here's a value, there you go. So the type is dynamic, it just gets determined at runtime. So as it says, variables are declared without types, and they can even change types. Sometimes that can be bad if you're not expecting it and the code's not prepared for it. That's okay. There's more versatility in having this kind of variable typing than if everything was strict. But because of these things, there's a higher probability of runtime type errors than statically typed languages. It's also not compiled. So when you compile things, the computer's got all kinds of time to look at all your variables, all your code, and do all kinds of stuff. There's a lot of things that compilers do, and they work to try to identify errors ahead of time. But Python doesn't know anything until you run it. So it can't do that. So you generally find errors in Python when you run it, rather than there's no compiling. And object-oriented language. So everything in Python is an object. Everything. Integer 1, that's an object. Actually, all the integers are objects. All the floats, everything there is an object. Okay, so properties and behaviors are bundled into objects. You can then create classes to create user-defined structures and types. Like with PySat, I have the PySat.instrument. That's a class. Allows me to produce another object, but it allows you to produce something that's altogether with a specific focus. And then instances are objects built from a class's blueprint, contain real data. So the class is the definition. And then like in my demos, when I said ACE equals PySat.instrument and stuff, I'm instantiating a particular instance of that class. All right, so how do we get Python? Python installations. Most likely there's already a binary Python executable stored somewhere on your computer. Operating systems themselves use Python. Mac uses Python, I believe Windows uses Python for stuff. Linux has already got Python. So you've already got a Python on there. Usually you don't want to mess with that one. You want to leave the system Python to itself. But still, a Python installation is going to include one is a bin folder with the Python executable. It's also going to include things like the pip package manager. So like you can do pip install PySat or probably pip install PySpeedas or all these other ones, as long as they're on PyPy. Pip is the latest one that will go out to the internet to this Python repository, download the program for you. It'll look at the requirements in there and it'll download some stuff as appropriate. Your Python solution is also going to have a lib folder and is going to be divided into like Python x.y. That's for versions. And then within that, there's going to be site packages folder. So that's going to have all the packages within your Python version. And when you install stuff like pip install, then it goes into the site packages. This is just a little bit of background to let you know. In practice, you shouldn't ever actually need to go find where the site packages directory is. When I first started with Python, I was messing with it because I didn't really know what I was doing. But once I got a little bit more up to speed, I haven't been back to that directory in, I actually don't know how many years. So Python allows you to pretty much ignore most of the things that are needed to get it running. And that's thanks to all the, thousands to millions of developers that have continued to build up the Python ecosystem to this day. When I first started, pip was kind of new. There used to be a previous version or iteration that was called Easy Install. And it also tried to make it easy to install things. There were some issues that the community identified with that. And as a result, pip came along, which improved it. Some people have identified some issues with pip, so there's some further follow-ons, but pip is still current anyway, and easy to use. It's possible, even common, to have multiple Python installations. Like I said, your operating system already has a Python installed, and it's using it for operating system stuff, okay? So when you go to install Python, you don't want to mess with the operating system Python because it's doing its thing. So you want to leave that alone. On my machine, I probably have 5 current installations that I have, different versions of Python or things like that. So I even maintain an older version of Python 2 series for some old code. Got a couple different at Python 3. So, it depends on what you want to do. Sometimes you find a package that does exactly what you need, but it was released 3 years ago, right? And maybe that maintainer is no longer active on it, but the package itself was really good when it was released. So maybe it's designed to run on Python 3.6. And right now, I think we're up to Python 3.11. So you could have a new installation that's just for Python 3.6 to do that, that package. And then for all your other stuff, you might want to use something that's more current. It's up to you, really. As I was saying, different Python versions are sometimes needed for different tasks, particularly with the OS Python. Changes to the OS Python are going to be slower than any probably Python installation you're ever going to find. So once the operating system people get something running, they don't want to mess with it because there's a lot of stuff that builds on top of it. So installations can be managed with virtual environments. So virtual environment just makes a separate section in your computer where you can install kinds of stuff where everything is going to work, but it doesn't interfere with all the different other virtual environments. And then you can easily just swap between and say, use this one. Now use this one. Oh, wait, now use this one. Okay, so technically a virtual environment are self-contained directory trees containing Python installations for a particular installation, a particular version of Python, also include packages and things like that. There it is. It holds its own set of packages, and it can be a very good practice to use a different virtual environment for every project. The reason being, say you're working on this project, everything is good, you get your results, you submit your paper, it gets accepted, wonderful, you move on. You start working on another project. Maybe a year, 2 years, 3 years from now, somebody comes along and says, hey, that project you're doing is really cool. Maybe we should collaborate and write a proposal and try to get some money to do some more stuff or something like that. Well, everything keeps just progressing in open source. So if you've got a virtual environment that you created with that project and you kept it, when that request comes down years down the line, you can just, hey, go back to that virtual environment and say, hey, do stuff, and it's still going to be there and it'll still run. Yeah, so it avoids dependency compatibility issues. And as I've already said multiple times, don't mess with your system Python. So if you're using virtual environments, you won't mess with it. And if you use the other Python tools, you're not going to mess with it really. But you probably have to go a little bit out of your way to try to mess with the system one. But I'll tell you how to avoid that. So how to install? There are a lot of different ways. And everybody I've talked to, at least on the PySat team, everybody's got their own way of getting Python. But yet PySat works on all those machines, so it's okay. So there's not, so I just recommend that you find the one that works best for you. One way to go is to download the official distributions from python.org. Just go right to the source. Okay. You can install from a package manager, something like called Conda. You can get specialized distributions for specific applications, in principle. The official distributions are generally the safest option, right? Because it's coming right from the Python developer, so you're closest to the source. Okay. That being said, I personally have never installed Python from python.org. First, you can check on your local system if Python is already installed. So you add a terminal, you would type Python space dash dash version. If you've got Python, it'll tell you. If you don't, it'll be like, I don't know what you're talking about. On Mac, Python 2 came pre-installed in Mac OS versions less than Catalina. I don't remember what version Catalina is the number, you know. It's no longer the case though, so that's good. Some things do progress. So if you download from python.org, it'll just download an installer and you can just click some buttons. And then before you know it, you're gonna have Python. For Macs, a good thing can be Homebrew. So on Linux distributions, there's package managers that hold all the different programs for that particular Linux that you're running. Officially, Mac systems are Unix, but because it's a Mac system and Apple doesn't have, Apple just doesn't put together a package manager. They just don't. They got the App Store. So these folks for Homebrew put together the same equivalent thing, but for the Mac. So it's a package manager for the Macintosh, and it gives you access to all the same types of things that you could just traditionally get on Linux. So here's an example of the Python installer on a Mac. You download it, you double click the installer, it brings up a GUI, you hit a few buttons, and before you know it, it's going to install it for you. If you want to install Homebrew, you can go to the web page, Homebrew, maybe it's .org. I don't remember the last one, but if you search for Homebrew, it should come right up. Question? No, so this, for installing Homebrew, this is going to install the Homebrew package manager. Yeah, this is just for packages. No, so you can actually probably get Python via Homebrew. It's a package manager. Yeah. So the way you install it, if you go to the website, it's just going to have a command on the website and says, hey, if you want to install this, copy this command into your terminal. And this is going to be the command. So you just copy it, go to your terminal, you hit paste, you hit enter. Maybe it asks you a question. I think the default might be yes. And then it's just going to do a bunch of stuff, download a bunch of things, and then it's going to be set up. When I go to install Python, this is the first thing that I do, especially if it's a new machine. I get Homebrew. The reason why is not to get Python is because I want to get GCC, or really I want to get Fortran support. So Apple, when the Macs, they come pre-built with compilers, but they don't come with Fortran support. And it, I think it still might even come with a new C compiler, but on the Mac it's not configured with Fortran. If you get it from Homebrew, then GCC also has the Fortran support. It used to be in G-Fortran. It used to be its own separate program, and then it got pulled into the full GCC. So like on this new machine, I just got this a few weeks ago. I went to Homebrew, I got it, then I did brew install GCC so I can get good compiler support, and then I could run things like OMMBV, which has a lot of Fortran. So after you get Homebrew, then you can do brew install Python 3. That'll get you the latest Python 3 on your machine. On Windows, Python does not come pre-installed. So it goes. If you write Python into the terminal command, though, it will take you to a Python store page as of the May 2019 Windows update. So that's probably nice. So it's the same type of thing. You can also go to python.org and get a graphical installer. You can get it from the Microsoft Store. Or what I would actually recommend, really, this is me personally, if you're running Windows, is you should go and install the Windows subsystem for Linux, or WSL. So I don't know how many of you actually think about what Microsoft does or what they used to do, but Microsoft fights a lot with standards. For them, it's a bit of a weapon. So they historically try to get their software enough to be a standard so that nobody else can compete, and they push everybody out. So it's pretty shocking for Microsoft to release WSL because it is just fully installs a full Linux installation on your machine so you can do open source stuff. it's basically them admitting that they have lost the open source standards war. Everybody is developing on Linux initially, and then a lot of Mac people were not using Windows. And then it also caused problems that Python would work great on Linux and Mac, but then sometimes on Windows things weren't so great, mainly because the Python developers weren't using Windows themselves. And it also made it harder to get other packages and stuff on there that would play nice with each other. So if you get WSL, you get a terminal in your machine that is actually Linux, and then you can just do everything the same way that you would with Linux within the terminal. So I think that's really the way forward. Here's a shot of what the Windows installer looks like. It's a GUI. You click a few buttons, and then you're going to be set. Here's what it looks like if you search in the Python for Python in the Microsoft Store. First one's Python 3.8. It's probably an older screenshot. WSL, as I said, allows you to run a complete Linux or a Linux environment directly in Windows. So that's really the way to go, especially for the history of science software. There's so much science software that was written back in the day, and that was on a Unix machine. If you want to be able to really run that stuff, then you want to be on Linux. Microsoft will tell you how to install it. It's pretty easy. And then once you install it, you can install Python like you would on any other Linux machine. That's really the way to go. On Linux, you can build Python from source code if you want. Alternately, each Linux distribution is going to come with its own package manager where Python and all that's already been built by the people that released your operating system, and they've tested it in principle and confirmed everything works. So, you know, if you get it from your package manager, then you should be good to go. That being said, I don't know how many flavors of Linux. There are a bunch. And each one has got their own different thing. Whatever it happens to be, some of them share things, some of them don't. So depending on which particular flavor of Linux, then your package manager command is going to be different. That's pretty much the only thing. The command for the package manager is going to be a different word, and then you probably just do install Python. Generally, though, with people running Linux, they tend to know what their package manager is, I think. Here you go. Here's a web page on python.org. You can go there and you can click on stuff to get the source directly. That's for Linux. You have to have the dependencies installed first if you're going to go that way. If you go the package manager way, it takes care of that for you. But here are the actual commands. If you're on something like Debian, Ubuntu, or like Mint, or something that's based or similar to that, then this is the specific command that you would run to get all the stuff that you need. If you're on Yum-based systems like CentOS, whatever, then Yum is the package manager of relevance. That's relevant. Okay, managing virtual environments. I've already said that word so many times. How do you actually get one? So there's multiple ways to get a virtual environment, and we're going to cover three. You got VMV, PyEnv, and Conda. All right. So VMV, this is the go-to virtual environment manager. It was bundled with Python as of version 3.3. So it's easy to use, and usually if something's easier to use, then it quite can't do as many advanced things. That's usually a design tension. That's okay. We've done some surveys over the years. Yeah, it's been years now. Asking PyHC to people where they get their Python and stuff from, and about 12% of people use VMV as their virtual manager. So if you want to actually create a virtual environment using VMV, either way, you do Python 3, right? Everything's Python 3 now. .m-m VMV, and then the name of the virtual environment that you want, like a project name, a date. Date's probably not the best way to go. Project names are probably better. That's up to you. Once you create it though, then you have to activate it. Say, hey, computer, use this virtual environment. So that's the source. And then you put your name, bin activate. That's just technical stuff. Once you do that though, then you're in the virtual environment, and the Python that you're going to use comes from that one. Once you're done, or you want to switch to something else or something, then you deactivate. That's just a command. And then to delete it, if you want, it's just a directory full of files. There's not particularly special, so you can just RM, right? Recursive, force, and then the path to the thing. You can also use PyEnv instead, so it's more complicated workflow than VM. It offers more features though, right? That's the trade-off. You install it a similar way. So PyEnv is the command, install for a new one. And then here the -v is specifying a particular Python version, give me Python 3.10.0. Right, so new Python versions are coming out all the time. 9% of PyHC people use it. Okay. This is what it looks like. It's just doing those commands. So you can check that out if you want. Conda. This is the main alternative to pip. Pip works really well with just Python. But there are a number of Python packages out there that include more than just Python. I mean, some of mine use Fortran as well, and C, and some other things. You can even have more complicated things. Pip doesn't do so well with those super complicated installs. So this company was formed, Anaconda, and then they're creating a system that's supposed to deal better with all those more complicated situations while also still being easy to use. So Conda does a couple things. It manages virtual environments for you, but it also installs packages. So it can be like a one-stop shop. You can install different versions, different Python versions, and pip only deals with packages. Conda can deal with more things. So just to tell you what I do, like I said, if I get a new computer like this one, which is just a few weeks, just got a few weeks ago, I get Homebrew. I use that to install GCC. So I get all my Fortran support. I get Conda, and I use Conda to install NumPy. And then from there, I do a pip install PySat, which gives me all the other things that I need, and then I just pip everything else. I just found that getting NumPy from Conda tends to be the most robust. So I just dally in Conda a little bit. I just need it for that first step, and then from there, I'm typically happy with pip. I do also use Conda to manage my virtual environments. That's just me. Conda does check for dependency issues before installing new packages. Pip kind of does. If you don't have the package and the thing you're trying to install requires it, pip will install it for you. However, if you already have a package that's required, but it's the wrong version or something like that, and the recent versions of pip, it's going to leave it alone. I don't normally have problems with that, but if you have a long running installation where things keep going, then sometimes stuff can crop up. I think there might be some options where you can force pip to do that, but by default, it doesn't. All right, so part of the larger Anaconda system, Anaconda is this company. Actually, it was formed by somebody who's coming out of NumFocus, all right, I believe. Most of the people in PyHC are using Conda. That's pretty good. So how do you make a virtual environment with Conda? It's Conda create -- name. And then you put the name that you want to call it. So pretty straightforward. You can also specify a Python version when you create the virtual environment. After you've created it, you got to tell your system use it. So it's got the activate command. Similarly, you can tell your system stop using it. And you can tell Conda to remove it for you too. So you don't have to go and do it manually. You can just use Conda. All right, so Conda comes from Anaconda. Anaconda is this larger thing, and we saved it for last because it's its own can of worms. Some love it, some hate it, or many love it, some hate it. It is currently the world's most popular Python distribution platform, right? So everything keeps evolving. I mean, originally, I don't think Python had anything. Then there was easy install, and then there was pip. There's other stuff. Now we got Conda. Each time the scale of the problems that they're trying to solve gets bigger, and the code gets more and more capable. Conda can build some pretty complicated stuff, is my understanding. Anaconda is focused on data science. So it's a Python distribution with a whole bunch of packages in there that are already, set up for science. So it's got like a lot of NumFocus and other packages. If you just get Python, you're getting the base installation, which is still good, but almost every package, if not every package that was talked about during this meeting, builds upon some NumFocus packages like NumPy. pandas, Xarray, SciPy, Matplotlib, Plotly, other stuff, I'm sure, right? So these are all much higher level. You can get all of these from Conda as well. So, and some of them come preloaded. I'll also offers a GUI and a Conda navigator, help you just download stuff, right? So here we got a variety of things like PyCharm Professional. This is IDE for development. This is something I'm currently using. I tried Spider out years ago. This is also another IDE. PyCharm does cost money. It can, unless you're a student or something like that. Some of these, we've been using Jupyter notebooks a lot or stuff like that within Helio Cloud. You can download all these things, just clicky. You can also download them from a terminal, but not everybody likes to do that. Different ways to look at it. There are a lot of packages out there. So if you haven't ever looked, you might just want to take a look at the sheer number. So Anaconda is like this Python plus all kinds of other stuff. So it's the biggest like file stuff that they distribute. Not everybody wants to download that because perhaps maybe they don't have the disk space, maybe they don't have the bandwidth, maybe they just don't want to. So there's a smaller version called Miniconda, which is still distributed by the same company, still got packages, just not as many. So Conda, as we were showing, is the main alternative to pip. Did I go backwards? Doesn't look like it, but I thought I already saw this. All right. Python packages. It's a collection of modules, so Python scripts that contain published functionality. Stuff that we're talking about here, packages. Packages tend to offer a unique tool set. They may have their own unique syntax values, syntax rules, so like AstroPy units. They have the developers made units. Units works in the way that it works. Nobody told, there's no restrictions. Like it's not like there's an official Python person looking over the AstroPy developers going, don't do that, or do this, or do the other. I mean, I'm sure the AstroPy community has its own rules for doing things like that, but it's not enforced by the outside. So for packages, it's just a free for all where developers can do whatever they want. One of the really nice things about Python, the way the language is written, is that these third-party packages can actually integrate into the first-party features of Python. So it's one of the reasons I think that Python is successful. Anyway, package management allows versioning, so you can update a package for one project, but not for another. That's good. Two main options for installing Python packages are pip and Conda. These are the current ones. Pip is the standard package manager. It is bundled with Python. So once you have Python, you have pip. It allows you to get new packages, which are good. It installs packages from the Python package index, or PyPy for short. So that's PyStats on there. I also had the RC on test PyPy, which apparently one step too far they didn't quite have to make, but they also have a test system. So the community's gotten together, gotten some servers up, infrastructure. Pip talks to the servers all well. Everything can come down. So it's the official third-party software repository for Python. If you want to install something, it's pip install and then the package. If you just do the package name, it'll just go get the most recent thing. But you can specify a particular version by equals and then put in the version number. If you want to uninstall, then it's pip uninstall package name, upgrade a package, and list all the packages, pip list. You can see the commands. Conda installs from various channels. So the default channel is maintained by the company itself. It tends to have limited package selection, right? The company has only got so many resources. So they probably focus those on the packages that they feel are the most important. It's going to be perhaps somewhat less up to date, but there's probably going to be more stable. Apparently they have GPU support and other things like that. So if you've got some beefy GPUs that you want to use for calculations, that could be a way to go. in practical terms, a lot of people use Conda Forge, which is a community channel. So it's the community contributing their own packages. So there's more stuff up there. It's going to be tends to be more up to date. To install with Conda, it's the same, very similar type of syntax. Conda install the package. You can specify a version number to get a particular one. Uninstall, you can update a particular package or you can update everything. That's nice. You can list everything. Pip and Conda, they do have overlapping functionality. They are not identical, even though you can do a lot of identical type things. Conda's, Pip are designed for different things. Pip is just for Python primarily. And Conda can install packages from any language. So I say it's primarily, Pip is primarily Python because Python packages can include some other languages, but it was those other languages that would tend to actually give Pip some trouble. Pip, you have to have Python for it to work. Conda will, can install it for you. Conda manages virtual environments and Pip does not. Conda will also check for all your dependency issues before installing new packages. So Helio Cloud was built with Conda, I believe. It was not, there is support for Pip. We saw a couple Pip commands in the demos. So you can do a combination of both. As I said, I start with Conda and then just go to Pip. Pip can install things from GitHub directly. For Conda, it has to be added to one of their channels. There are over 150,000 packages on PyPy. That's a lot. I don't know how many there are for IDL. MATLAB has got their things, but there's not 150,000 of them. The toolboxes, right? Toolboxes cost money. Pip packages don't. Conda has closer to a few thousand. I don't know how many packages that you need, but they're both there, so you don't have to necessarily pick one. So what about PyHC packages? We've got over 60 and growing. They're listed at heliopython.org/projects. We are working towards interoperability. The community wrote down and voted on standards. So we do have standards and we are working on enforcing them, and it's right. So it's a long-term interest, not just for PyHC, but the entire scientific community. If our science packages are high quality, they're just going to have to be high quality. Otherwise, the science isn't going to be good, or people won't be able to use them effectively, or something like that. So we are open in PyHC to accepting all kinds of packages. You just have to make sure that you put in the legwork to make sure the package is high quality. So what are the standards? Perhaps I'm not going to go through all of them or anything like that, and it's too small to read, but it is up on the website. But it's just designed around making sure that packages are readable. So I forgot who said this, but many people might consider that the purpose of code is to run on a computer, right? It's software. You're supposed to run it. It's supposed to do stuff. But code is really there to be read. That's the big thing about open source versus closed source. With open source, you can go and read the code. That's where all the ideas, all the things are. That's really what it's about. And if other people are going to be able to comprehend that, then it needs to just be organized well, and needs to be documented, things like that. So it's got to be packaged. PyHC things need to allow open development, certain restrictions on releases and operating support. Needs to be an open source license. Coding style, we're enforcing PEP 8 in general. You need documentation, you need testing. Unit testing is huge. Probably spend more time writing unit tests and things like that than the actual code. Took a lot of time on OMMBV and on PySat. For PySat, there's definitely more lines of unit test code than there are actual PySat lines of code. And that's because PySat has a lot of options, and all those options, you need to make sure they all work together. Anyway. Dependencies should be minimized. Things should be on Python 3. We shouldn't really be duplicating stuff. We should collaborate, limit binaries, and code of conduct should be there. All right. Choosing a Python platform. Now, where do we write our code? There are three main options. You can write it right in your terminal. You can get an integrated development environment like an IDE. So like MATLAB, if you've had a MATLAB, or IDL, they come with IDEs, right? It's a user interface. You can click stuff. It's got like a file browser. It's got text windows where you can type your code. You click buttons to run it and stuff like that if you want. So you can get those. Spider is free. PyCharm is out there too. I'm sure there are more. Or you can run it right in a Jupyter notebook, right? So you can just run it right in a web browser. So Jupyter is a new technology, which is pretty cool for that. How do you write stuff in a terminal? First, you're going to activate your environment. Then you're going to do touch script.py to make the system happy. And then you can use your particular text editor of choice. In this example, it's Vim. So open up the script.py. You can just write print, open parentheses, quote, hello world, quote, close parentheses. So it's just typical for almost any language to have the demo, how do you write hello world? And for Python, it's about as short as it gets. Just one line. And most of the characters are just hello world. So you don't have to define a function or any of that stuff. It's just boom, right? So developer time is optimized. And then if you actually want that thing to run, then you run Python. Python is the executable, and then you point it to the script that you want Python to execute for you. All right. So good choices for an IDE. For Sean, Spider, that's one that was up on the thing. It's free. PyCharm, that's the one I've been using. Visual Studio Code from Microsoft is also a way. So IDEs tend to be more general than a particular language. So if there's an IDE you like, most likely it'll probably support Python. And depending on your IDE, you can have all kinds of features like syntax highlighting and all kinds of other things like that. Just depends on how you want to do it. The same, your favorite IDE probably already offers Python compatibility. We've been using Jupyter Notebook throughout the summer school on the Helio Cloud platform, so you can just run stuff directly in a web browser. And as demonstrated directly with Helio Cloud, when you do that, you don't even have to be running on your own computer if you don't want. Python can be set up and Jupyter to actually execute all the commands and stuff like that on a remote machine. Or you can run Jupyter Lab and run the machine run the code just on your own machine. That's it. So thank you for your attention. Are there any questions?
Awesome. Thanks, Russell.
Sure. Please.
I think Sean had them locally. I'll make sure. I think
I
that we
have
can
the
just,
link.
yeah, maybe you can throw it in general.
I can do that.
Yeah, thank
I'll
you.
post it in general.
Or in the Python session, learning, whichever you want.
Everywhere.
Okay.
Don't want anybody to miss out. Thanks for the question.
Yep.
Any others? Yes, Ruth. Mm-hmm. Well, so the
Can
step
you
there is
repeat
you
what
need,
she said first?
oh, right. So if I can summarize, Ruth was as saying she was surprised that she's hearing that having multiple Pythons on a system is a good idea because in her personal experience, she had some problems. Is that, yeah, okay. To avoid those problems, that's where you want to install the virtual environment first, because it kind of keeps each Python in its own little silo and it keeps them all sleeping until you specifically go over here. And then it keeps the operating system Python, doing its own thing, so you don't mess with that one either. In practice, I really mostly only ever have one virtual environment that's active at a time. I haven't found a need to have a bunch, but it's an option. Yeah, good question.
If you have any further questions, feel free to post them in the Python Learning channel. Thanks again, Russell.
Thank you. Cheers.
All right. On to John. Are you talking, John? That video? Oh, no. One moment. I think he's logged out and logging back in. Okay, we have John again.
I'm going to take that as a no. What's the next thing I can punch here? Okay, can you hear me now?
Yes.
Alrighty. Yeah, I wound up with two problems there. One was Zoom just wasn't looking at my microphone, and then once it was, it decided I was being too loud and turned me down. So, apologies for that. Now, can you see me?
Yes.
The next question. Ooh, that's getting even better. Okay, so one more thing we've got to make sure of here, and then we'll actually be able to go somewhere. Can you see my screen now?
Yes.
Fantastic. All right. So, ironically, I'm going to be talking about some ideas regarding testing, which I guess testing your audio helps. So Russell mentioned this, and this is going to be kind of a whirlwind tour of a couple of the concepts behind testing in Python before then digging deeper into some broader ideas of software engineering. So first, what do we mean when we talk about testing? Well, there's a wide range of forms of testing, ranging from unit testing, where you're testing really the smallest possible chunk of code at a time. That's usually automated. It's usually structured or formal. And by formal, I don't mean mathematically formal proof, just that you have it explicitly structured, explicitly planned to meet a goal. Functional testing or integration testing, which I'm lumping together, it's a little inaccurate, but they're similar, where you're not testing the smallest possible piece of code, you're testing some combinations of code that work together. Again, usually that's automated, it's structured in some way. That's really the focus of what I'm talking about here. There's also acceptance testing, which is quite important. That's human-driven. It's testing the system as a whole and making sure that it's suitable for the use of the person it's intended for. Again, there may be some automation. It's usually structured. And most of the time when somebody says, well, I've tested my code, they mean something more like down here, the ad hoc, where you're testing the whole thing. It's often not automated, and it's often not particularly structured or formal. So it's just oh, I ran it, it works. That has some limitations. If they just say it's tested in that regard, well, okay, if you ran it, what did you run? How much of the code? What inputs? Where did you run it? Is somebody else able to do it too? And what do you mean by it works? There weren't any errors, there weren't any crashes, or does it actually mean the output was correct? And who decided what correct is? So if somebody just says their code is tested, you have to take an awful lot on faith. But if there are actually tests that you have that you can run, that you can examine, then you have a much better idea of what that code is going to do. So test generally consists very simply of three things. There's some sort of starting state or preconditions, you can say. There's some action that's actually running the code under test, and there's post conditions, so you can check what that final state is. If you've got a simple mathematical function, that's pretty easy, right? Your preconditions are the arguments. You're passing in a couple of things. Your action is that function call, and then it returns some values which hopefully match what you expect. Even in this simple case, though, there's quite a bit you have to think about. So the code is being run. Is that action actually hitting all of the code in the function? So we call this coverage, or code coverage to be specific. But if that behavior of that function depends on exactly what arguments are coming in, are you also testing this as a reasonable set of data? Do you have good data coverage? So if you have a function that just adds 1 to a number and returns a number out, you can get good data coverage pretty easily. You have 1 or 2 numbers, that's good. But say if you're treating positive and negative numbers differently, and all of your test inputs are positive numbers, then you don't have a really good test. So as I said, this is the simple case where you're just dealing with a function call, but it gets a whole lot more complicated than that. So your preconditions might be some data members if you're testing a class. It might be files on a disk. It might be some database records. What you do might be function calls. As we said, it might be an instance method in a class. You might be making a web request. You might be looking at mouse movement. There could be a whole lot going on. And what happens afterwards with your code, there might be, again, your class state might change. Stuff might go to the screen. There might be more database records. So if you want to be really specific, you can say, or really comprehensive, I should say, all your preconditions is the entire state of the universe before the test, and the post conditions is the entire state of the universe after the test. And hopefully you aren't actually in a situation where you care about that. Sort of the pathological case is if you say your precondition is all of the data that you're using for your entire study, the actions you're testing is all of your code, and the post condition is your entire publication. This doesn't buy you much. So please don't do that. And we'll talk about why. If you're doing those, the unit testing, where you're testing individual small pieces, that really helps you isolate a problem. It also helps you avoid the pathology where one part of your code is wrong in one direction and the other part of the code is wrong in the other direction, so you don't see it come out the end. It minimizes the interactions between code. I know we often like to talk about reductionism as a bad thing and trying to think holistically, and that's an important idea because systems don't behave the same in isolation as when they're interacting with other systems, but that also makes it more important to get that isolation first so that if issues come up in the interaction, you know it's in the interaction, not in those individual things. If you're doing the unit testing, you're getting the sum of the preconditions. So maybe you're getting the data coverage with 3 different inputs for one function and 3 different for another function. If you're doing that unit test, you kind of have 6 things to test. If you're doing it end to end, you have 9 things to test. You have the product. And you can see that quickly gets terrible. So it lets you get very comprehensive coverage without having to go into this big Cartesian product. And finally, when you're dealing with a unit test, you're often dealing with a very small piece of code. You can probably have a good idea of what the output really should be. And so you can actually put those expectations in your test and know that you're getting the expected result. It's much harder if you're testing a great big complicated system to know what the output should be. Because if you knew what the output should be, you probably wouldn't be running it, right? It just wouldn't be of interest. So a good end-to-end test is still valuable. Those integration functional tests are great, but if you're building on that foundation of good individual unit tests, you have a much better idea what's going on. So what do they actually look like? I've been talking just conceptually. The good news and the bad news is that tests are basically code. So there's code that sets up those preconditions, calls whatever you're testing, checks those post conditions. You can do this yourself. You can just write something, declare it a test script, and push it all around by yourself. But if you're using a testing framework, that gives you a lot of support, both for this part of the pattern and a bunch of stuff that surrounds it at a higher level. So running all of your tests, making sure that individual tests are isolated from each other, getting nice output. So Python has a number of unit testing frameworks available. There's one called Unit Test. This is built right into the standard library. It comes with Python. It's based on XUnit, which is a really common style of test framework. It's been implemented in most languages. It's really the foundation of the modern idea of unit testing. But even right in that documentation, there are links to several other possibilities that you can consider if you're interested in poking around. Two of them that tend to come out a lot are PyTest and Nose. Feel free to look at it. I'm going to talk about unit test because it's pretty straightforward and it helps illustrate the concepts. These other frameworks also are generally designed to function well with unit test. All right, so the structure of this, there's an overall test suite, which is one great big script that really holds everything. And I'm not really going to distinguish between a suite and a runner. That's getting way into the weeds, just be aware of that. Within each suite, you can have one or you can have more test cases. Those are classes. The name test case I feel is a bit confusing because I usually think of a case as being a fairly granular thing. It's actually a number of things that are kind of related to each other. That test case can have one or more methods, and those are the really independent portions. So that method is what kind of sets up your precondition and your execution and your postcondition. And then these assertion calls are made within the method, and that really is checking your postcondition. And so you can say stuff like, does this equal something else? Does this list contain this element? Now, those test methods can have a whole bunch of code in addition to the assertions. The classes can have other methods, other data members, but the core of it is the test method and the assertions in that. So just to see what it's like in code, this is the only actual code you're going to see in this. This is right out of the Python docs, and this is a complete, perfectly valid test suite where you have one class, that subclass is test case. You have 3 methods. Each method then has a couple of asserts. So if you run this script, this is the output you're going to get. It's going to say it's run 3 tests and they're fine. You get, note there's 3 dots here. There's one report out for each of the methods, even if there's a lot of asserts. So that method will end at the first failure. If an assert fails, if there's an on-call exception, that's the end. And that's why you don't put everything into a test method. The point of the unit testing is to know what thing works. So if more than one thing is wrong, you'll have multiple ones fail. The other thing to be aware of is that a function that does absolutely nothing is considered a good test. That's no problems detected, not actually good. So Claudio was asking, yeah, who tests the test? And this is where it comes back to being important to think in terms of a small enough unit of code under test that you can know what the output is. In the grand sense, we get into much bigger issues of your code being shareable and readable by other people who can then check you, and we will actually come back to that very shortly. So these are organized as classes. Why is that? Well, a test class can group together tests that are independent but related to each other. They have support for running the same block of code before and after each method, called the setup and the teardown. They allow that class to hold helper methods, so your test methods can call out to other methods. That's fine. And inheritance helps you be able to reuse code effectively. So in SpacePy, we now have 2 backends for coordinates. Our unit tests, there is one class. It has a bunch of tests. It has a single data member, which specifies which backend. Then we have one more class that just inherits from that, changes that data member, and then we get all of those tests running on the same backend without doing any rewriting, without doing any copy paste. So get started with the testing. Honestly, just putting together the stupid script that does the imports and does unit test.main, it gets you past that blank slate feeling, right? So you can actually have something to plug into. If you start doing some simple tests, that helps. Really, like any good coding, this winds up being learned by doing. So if you start by writing the tests that are easy, the ones that are simple, that will get you into the frame of mind. and then you can move into more complicated testing problems. Reading other code is always great. In this case, the test suites give you a very good idea of how to solve problems. I'm linking the PyCF test suite, not just for ego, but because it's a fairly simple thing. It's wrapping a library. It has a whole bunch of functions. There's not a big end-to-end set of interactions. But any of our PyHC core projects have very good test suites. They're worth reading. So I've talked about how, but the bigger question here is when should you actually delve into doing this testing? And that gets to a much bigger issue that I want to talk about a little bit. And that's, what does it mean to be thinking in terms of software engineering in the context not of delivering software, but of doing research and delivering science? This is wildly informal. I hope this is more motivational. If it winds up being a bit educational, that's great too. I'm not going to talk a whole lot about the how, but I hope to give you some idea of the why for bringing in some software engineering practices and the when, so you can make some good decisions about when you spend time on code and developing yourself as a programmer in addition to a scientist. So let's talk some definitions. I said software engineering. Okay, software engineering is, you can think about rigor. You can think of all the stuff that you should do. You should write tests. You should write documentation, as if it's this moral thing. But what I want to talk about is the results. What does this rigor buy you? And what does the failure wind up giving you problems with, right? So I say research context as the other half of that. The assumption here is that your goal is to publish results. The goal is not necessarily to publish code. So a lot of us running this workshop are developers for PyHC. In the context of our projects, we're trying to deliver code that will support the science. What I want to talk here is really to doing science with that code in your own code. So it's mostly to help you. If you wind up with research code that's shareable, maybe via one of these PyHC projects, great, this will help you do it. But ultimately, goal here is for you to publish papers. The code's a means to that end, but it's still worth taking care of your tools, right? This is from Adam Savage's book. He has pictures of just the amount of effort and detail he goes through to keep his tools organized. And this is not because he has a lot of time to faff around when he's working with doing special effects builds. It's because ultimately this is time that he invests to make sure he can be more effective. So in the research context, what do we get from doing this? Well, it helps us deal with paper revisions, right? If your code is in better shape and you need to make modifications because you got some review comments back, you'll be in much better shape to modify that. You'll be in better shape to build on the work that you've already done, publish more papers, to go on to do new studies, which might use some of the same techniques, address this idea of reproducibility we keep talking about, and in some cases will help you with the journal requirements. Journals will often have requirements for data or code availability. So the real goal here is to give you some ideas for minimizing the hassle in doing this and maximizing the return. And another way to think about this is if you're thinking in terms of reproducibility, reusability, being, having a happy life, where this all overlaps is stuff like, well, I submitted this paper 6 months ago and now reviewer 2 is doing reviewer 2's thing, and I have to change all these color bars, and I'd rather not have this take up my entire time. Underlying this talk are a bunch of sources. Some of this is more specific citations that directly went into this, but most of this is some inspiration for ways to code effectively that have affected the way we think about code. So yes, painful experience is definitely a part of this. I would recommend you not take this as your own resource. Use my painful experience instead of going and having your own. But you can do it if you want. I highly recommend reading this article, 9 Steps for Quality Research Software. And broader resources, Q is the magazine of the Association for Computing Machinery. It's their practice magazine. It's not about theory of computer science, but application. There are a couple of blogs by developers, and the US Research Software Engineer Association. It's another good resource. So some lemmas, some ideas that kind of underline the recommendations I'm going to have. First is code as inventory. What I mean by that is code's value is in the function it provides, not in piles and piles of code just for code's sake. All right, you want to be doing things with it. Second is code is read more often than it is written. Russell mentioned this. Hopefully, it'll be run more often than it's read, but you read it once and you wind up reading it a lot, which means you have two audiences, the computer and the person who's trying to use it and understand it. And that means that the code can kind of be explanatory of what it's trying to do, but it's also often harder to read than to write. If you're doing a code product, that is something that is meant to be used by somebody else, not just a one-off, that usually requires about 3 times as much effort as something that just works. So this is one of the earliest representations of this idea. You can see this is only almost 50 years old now. You could also think in terms of the usual WAG that first 80% of the work takes 80% of the time, the next 20% also takes 80% of the time. If you've got something that is good for your research and you want to get it to a position that somebody else can use, you're going to be doing quite a bit of work for that. And so why even bother? Well, the alternative is we keep writing the same thing over and over again if we don't do this, and you keep making the same mistakes. So the goal here is to help you focus in on what of this additional work gives you the most payoff. One final concept I want to introduce is code smells. You could consider this a noun phrase or just plain a sentence in itself. So code smell is what we call a hint that something is wrong. So think about when milk goes bad, right? You can smell it. You're not really doing a deep analysis, but you know there's something here that tells you it's no longer nutritious. This ability to sense code smells often comes about through experience, but people tend to share it around in the coding community so other people can benefit from that experience. Again, if you can manage to not have your own painful experience, that helps a lot. So I'll mention code smells a few times going on. So I'm going to tell you one thing. If you take away nothing else from this in the way you write code that does your analysis, do version control. Good version control is your lab notebook. That's going to give you the record of what you did without having to write it down. And it's pretty awesome because if you're working with code, your record of what you did and what you actually did are the same thing. You're not having to write down procedures. But when you're putting this into version control, you're going to have a commit message where you can record why you did it. That's, again, connected right to the actual what. And it's going to record when. Once you have your code in version control, that gives you the freedom to experiment with trying new things without being worried you're going to break things. If you remember something you did a week ago that actually seemed like a bad idea at the time that now you want to try again, you can go back and dig it out. All right. So if nothing else, use version control. Now, a lot of people will start doing things where I don't want to do version control. I'm just going to make a copy of the file and it's going to be code.py_2022-0101 and again and again. At that point, what you're doing is you're basically doing version control yourself. All right. And again, old quote, if you can't remember the past, you're condemned to re-implement it, often poorly. So it's better to bite the bullet, jump into a real version control system, and then you get a whole bunch of support for this. You can easily go back in time, look at when you did things, what changes you made, why you think you were doing that. All right. So a couple of quick tips. Use Git. I don't think there's too much reason to use any other version control system if you don't already have one. It's very widely supported. There's good documentation. There's lots of tools. You can just work it right on your computer, unlike CVS or SVN, where you have to set up a separate server. You don't have to do that. And it's very easy to go from a project that you work with yourself on your computer to sharing with people. And so you can scale up that complexity as you go. Make your commit small. If you got something that works, make the commit. Do a note of why you were doing that, what changed, and you can really focus on the single user. There is Git documentation all over for merge commits and conflicts and pushes and pulls and all that. When you're working on your individual research code, that's less important. Now, once you start contributing that to other folks, then you can start learning how to do that. You don't need to know that up front. What goes in version control? Any code that you write that's actually relevant to your analysis to do your final results, right? If you do some interactive noodling around and come up with a result, you want to try to capture that. We'll talk about how. Having the code that makes your figures is great, because in that situation where 6 months later, somebody wants an axis label changed, you can easily just go in, change that, boom, you're done. Any information about dependencies. So if you use pip and you have a requirements.txt that saves the details of your dependencies, great, put that in. The things I don't generally recommend putting the version control, don't put the actual data in, because that's generally big and static. It's not changing. Hopefully you're working from that. Make sure you have a backup of it, but don't put in version control. Don't put in the actual dependencies, so don't go and check NumPy in if you're using NumPy. There's not much point. The figure outputs, again, tend to be big in binaries. In theory, you should be able to get those just by going back, running your earlier code. Something to taste, the actual manuscript of the paper. If you're a LaTeX person, honestly, put in version control. It works great. I do that if I'm writing a paper in LaTeX. If you're doing something with a binary format like Word, you get less benefit, but make sure you have some way of preserving history. I wouldn't necessarily recommend going and setting up a full SharePoint thing. It seems a bit overkill, but have something, right? One of the manifestations of this is the executable paper idea. Several of us are doing that for a PyHC paper, where the main paper is actually a notebook. And so the code and the manuscript are actually kind of the same. And in that case, use a text format for the notebook, like Markdown, which JupaText will give to you. Get it in version control. Claudia recommended Overleaf. Overleaf, I believe, actually does have Git backing, so that makes it really nice. So it's a great thing to have. Which brings me into actually right on the next topic, which is laziness. Laziness is a virtue. So one of the big ways to be lazy in a good way is anything you're doing that's repetitive, you want to try to generalize. I generally figure if you're doing something more than twice, you probably don't want to copy paste it, because it's going to, in the long run, become very difficult to keep that in sync. If you've copied it a couple of times, you find you wrote it wrong the first time, then you're fixing it 3 places. So just generalize it. It also makes it very hard to read if you have 3 separate chunks of code that all do exactly the same thing. The fact they're different chunks of code makes people think that there's actually something different, right? The other thing about doing things repetitively, if it's tricky to figure out once, you're going to want to isolate it to make sure you got it right, right? And so, again, code is inventory. If you can use the same code to do multiple things, you're going to save work in the long run. And pretty much almost everything else in this talk is about enabling this generalization instead of duplication. And refactoring, documentation, testing, we'll talk about all of those, support that. So the ultimate laziness is use other people's code. There's often some effort in learning how to use other packages where it's applicable. That's what the summer school is all for. But you can avoid reinventing the wheel. You can use stuff that's validated, that's tested, that's ready to move between environments. This is really why we have PyHC. So I've talked about generalizing stuff and moving it out. This is a manifestation of a bigger thing, which is you can start to increase your software structure as you go. And the underlying concept here is what's often referred to as abstraction, where you're thinking about something on a higher level. You're kind of re-chunking from the level of individual instructions up to how they work together. And that's really the essence of quality programming. It's been argued that's the essence of computer science as a discipline. In order to do this, you start taking on structure like functions and classes. If you're starting to put blank lines in your code between chunks, you're thinking in these terms. So that's a code smell. You should start moving into higher level structure. All right. And if you can get your black boxes working right, where something has a function that it does and you don't think about the details, then you can be thinking about your science instead of your bits and bytes, right? Here's the tricky part. Abstractions tend to leak, as it said, where some of the wires start to stick out of your black box, all right? Doesn't mean it's not useful, but just be aware of that. And partly it's a question of what interactions have you figured out to make things general and what interactions have you missed. Of course, the important thing is when you're writing your paper, you don't necessarily have to be perfectly general, just generally enough, right? There's this notion that software is kind of fragile, that if we built buildings the way we wrote programs, the first woodpecker would destroy civilization. Part of that is because fragile software is weirdly robust in that if it is stressed in a very particular way, the bugs have been fixed in that particular case, it'll work just fine. As soon as something comes along that's slightly different, that's really solving a different subsystem, a different subset of the problem, then it will blow up. So those special cases are really what makes general code general, and it's what makes mature software look complicated. So if you throw away mature software because it's got all these, well, honestly, the wire's sticking out, then you've kind of lost that accumulated wisdom. It's better to refactor instead of restart. So we'll talk about that. The big thing is to know when you're trusting the abstraction and when you're thinking about its leakiness, right? And this is what the testing is for, so that you think about leaks when you test, and then you trust the abstraction when you work on a higher level. I'm going to talk very briefly about object-oriented programming. If you're building objects, so classes, those don't have to be concrete objects. The important thing is that they become abstractions that hide the appropriate amount of detail. So the code lives the data it works on, related code stays together, related data stays together. Everything inside the class interacts a lot, but doesn't interact a lot outside. This doesn't mean object-oriented is the one true paradigm, but this basic idea of what goes together is a good one to think about regardless of how you're approaching it. All right, so I've mentioned the idea of structure. So how do you what's the right way to do it? The nice thing with Python is that you can actually start scaling up the structure and going up in complexity pretty organically. So you start with using IPython and you're tapping away, and you realize you've got some stuff that's good. You can actually copy and paste that out of your session. If it's scrolled way back, there's this history magic command where you can actually just dump back everything you did. So you can start dumping that then into a script or just a single file of imperatives, or a notebook for that matter, right? Where it's a sequence of stuff, but you're holding on to it. And you start realizing what you want to call again, and you start putting that into a function. So the fancy word here is refactoring. You're rearranging the code without changing its function to make it more flexible later. And the testing is essential to make sure that that function isn't changing. So you might wind up with your functions interacting in ways that makes obviously going to classes. Then you might start going into modules. You have multiple files. You don't need to have a full package to be worthwhile, right? You're not necessarily going to be writing an installer for the particular study you're doing for a paper. Because if you have a bunch of Python files in one directory, you can import them from each other. You don't have to install anything. Just you have foo.py and you have some other file. You do import foo, that comes in there, right? So when do you start moving up this scale? Basically when you can't keep things in your head, right? So the 1-to-many rule is pretty useful too. If something needs to be pulled out, that usually means you're going up a level in structure, right? A little bit aside, talking about environments, reproducibility. So this is environments like Conda environments, VNVs. Sometimes there's this idea of, well, if you need something to be reproducible, to be flexible, you just want to containerize it. Put in a container and make sure everything is stays the same. On another level, you can talk V&Vs, conda, having requirements.txt that minimizes the changes of interactions around you so that you know exactly what versions of dependencies you used. You're not going to have a new NumPy show up underneath you that you didn't expect. If you focus just on containerization, what happens is those wires sticking out of the box stay sticking out, and you're just kind of moving the whole mess around. Eventually, you turn into the Carl Sagan quote, right? Where if you're making an apple pie from scratch, you have to create the universe. You can't containerize the entire universe. Also, I showed you a tutorial earlier this week that was built on work I did in grad school. When I was in grad school, we called this a phone. So the world has changed a bit since then. We want to make sure that our work can stay relevant. So containerization environments, they're great. They make sure things don't change when you don't expect it, but you do have to still be flexible and be able to move between environments. So when I say reproducibility, what do I mean? So if I just hand you a result and say, trust me, that's not really good science, right? You want to be able to verify it. If I hand you a computer and say, push this button and the result pops out, have I really improved on that, right? You need to be able to verify the result, validate it. That means you need to be able to go in and see the individual pieces. That often winds up meaning changing it. So ideally, code should be robust to those changes, and you avoid this "you break it, you bought it" policy, right? The other thing is that if you're reproducing something, that's almost always the first step towards then extending it. Maybe you're putting in more data from the same data set, or you're using a different data set, or using a new technique. So you want to be able to use your modern computer, you want to be able to use the latest NumPy. You might even have two different research codes that might have been containerized differently if somebody was only thinking in terms of containerization, right? So you want to make sure that stuff can migrate along through life. So this is, I'll talk about this in terms as kind of resilient reproducibility, where you're getting identical or equivalent results in different environments with different people, and ideally with a reasonable amount of effort, right? That there will often be effort in moving to new environments, but if you do things carefully, you can minimize that effort. So you can think in terms of minimize those complicated interactions, make sure it's the code's comprehensible. We'll talk a bit about that, and have tests that will verify that things work when you move into a new environment or isolate it when it doesn't. So again, this whole talk is really about ways to make your code reproducible in this way. So where do you worry about this resilient reproducibility, the ability to move? Usually you're going to find out just after you should have worried about it, where you'll have tried to go to another computer. So think in terms of how do you test stuff out before you give the code to somebody else. That's a good point to go poking, trying in different environments, before you submit to a journal, before you go and get that new laptop. Right. So one good way to support this is documentation. Again, code's read more often than it's written. If you do that structuring, you can understand it better. Documentation's an additional way to help. We've got this joke that if you're debugging a problem, you explain it to the duck. I actually have the duck. And once you've gone and broken things down and talked in plain language and dropped away all of your assumptions and talked to the duck, you'll often figure out what the problem is. That's a great way to write documentation too, is make sure that the duck can understand what documentation you're putting in. Because all documentation that you write is in some way for somebody else, because future you is indeed somebody else. You are not going to remember everything in the future that you know right now. So if you ever want to use your code again, it has to at least somewhat work for somebody else. So what should your documentation do? It should answer some questions. It should answer, what does the code do? Or what does the code not do, right? What are the caveats? Why does it do it? What trade-offs did you make in the implementation? Generally, don't put how in documentation or in comments, because you should assume the person reading your code knows the language you wrote it in. But they might not know every detail of the domain. But if you find yourself writing code that is so complicated you need a comment to explain what it does, that is a code smell. And you should be thinking about ways to untangle that if you can. If there's something particularly weird about the problem, make sure you include that as well. So code documentation, they go together because otherwise they will tend to diverge. If you make your code clear, you minimize the documentation you need to update. If you keep them together, that's another way to make sure that they don't diverge. So they should be in the same version control. In Python, ideally you have doc strings that glue the documentation straight to the code. So PEP 257 really describes standards for doc strings. Just do that. That's the main thing. You should have that doc string for any function or method describe what it does, little, one line or a little bit of detail, your inputs, your outputs. Examples are great. I strongly recommend using the NumPy doc standard. It makes things very clear. So when should you document? Writing these doc strings when you start to formulate a problem is often great because it helps you frame that problem. If you've just finished the implementation, it's a good idea to go and check and see if the documentation is good. And whenever you realize something's obscure, obviously put that in. Style, how does that help? This is really the third way. So computers and people read the same code and they read in very different ways, right? The computer either cares about something a lot or it doesn't, like most white space. People can figure it out if you're being a little bit weird. If you have a consistent style that minimizes your effort, right? So it means that you're not spending a lot of time thinking about the way the code looks. If two pieces of code look the same, they're probably going to act the same because you're not having differences that aren't relevant. It really lets you focus on the substance of the code. Again, the majority of this is PEP 8. That's a list of standards for white space and that kind of thing. If you follow PEP 8, you're being consistent with yourself and also with what general practice is in Python. So that helps a lot. If you're using what we call idioms, so this means something like using list comprehensions instead of for loops. If you use a list comprehension in Python, it makes it very obvious that what you're doing is building a list. A for loop can do a lot of other stuff. There's Pylint, and there are other things that are static style checkers that run on the code. They're great to have. Use a config file if there's stuff that doesn't really matter to you, and don't go doing convoluted stuff just to make Pylint happy. If Pylint is complaining and you wind up doing convoluted stuff, that is, again, code smell that you have painted yourself into a corner somehow. When do you actually go and spend the time editing for style? Ideally, you write to style the first time because you can waste a lot of time fixing for style. So run Pylint right off the bat. Other good times to think about this, if you're about to refactor the code and rearrange it, you might want to punch up the style a little bit first. If you have a piece of code you're generally confused about, I find going in and, well, let's get the white space right and this and that. Make sure the lines aren't too long. That's a way both to make the code a little more readable and also let you get your fingers in it and start to understand it. Style edits look terrible in version control because there are a lot of little changes. So try not to mix style changes with stuff that is substantive. All right, testing. As we mentioned earlier, you really want stuff that's repeatable, that's unit testing, and ideally is at least structured in some way. The repeatable documents what you tested, what behavior is expected, lets you catch those regressions, and gives you that flexible reproducibility. When should you test stuff? If you've broken it out because it's been journalized, done multiple times, that should have a test. If something has proven to be a problem, if you had a hard time getting it right, put a test in there to protect yourself. If it might encounter the unexpected, if there's something you sit up at in the middle of the night and go, oh crap, get a test in there. If you're going to change or refactor stuff, that's often a good time to go in and test. If you think it's too complicated to test, again, code smell. Think about refactoring your code for this because that implies there's a lot of hairy interactions. And it's pretty hard to know you really got your code right if it's too complicated to test because that means it's complicated. At a minimum, make sure you have a fairly structured functional All right, I don't have time for details of this, but go and look at coverage and go and look at gprof dot. Coverage gives you just that, what lines of code you hit. Gprof gives you how your code calls itself. All right, one more concept I want to bring up, which is technical debt. Just like financial debt, the idea being that you gain benefit now from money you expect to get in the future. Well, technical debt is work that you've pushed off later to get stuff done now. Like financial debt, it piles up and you spend time maintaining it and starts to soak everything up. So stuff we've mentioned that kind of falls in this general idea of technical debt, if you've got unreadable code that you've fixed by commenting it, if the testing is inadequate in some way, if your abstractions are leaking all over the place, if your code is fragile to different environments, all of this stuff is technical debt. You can get away with it for a while, but eventually making progress around the problem is going to take more time than fixing it. But it's still useful. So some ideas on when you accept this versus paying it off. Is it going to be easier to do it now than later, right? If you're going to forget something, it's probably better to pay that technical debt off now. But if you're in the middle of something where you're trying to think at the scientific level, maybe you'll just make a note and go, okay, I'm going to come back to this if it matters later on. If you're at a breaking point, maybe you go ahead and address the technical debt. If you can throw your code away and not start over, if you're really convinced you're done, then there's maybe not much point in really cleaning it up perfectly. Although that's pretty rare that you can be guaranteed that. And really the biggie is this technical debt something that's become an obvious drag on getting stuff done? Then you do want to put in the effort to clean it up. Again, it's perfectly fine to accept this, to not always do everything perfectly, but you need to make sure this is a conscious choice that you're making, right? All right, so conclusions, just the quick takeaways. Do version control. Use the quality libraries instead of writing yourself. Test stuff so you can be sure you can trust it. Make sure you can adapt to change. Read something when you write it so that you can double check, make sure it'll be readable again later. And develop that nose for the code so that you can, and then trust it. So if you start feeling something's hinky in your code, go ahead and take a look. All right, do folks have questions? I'm not seeing anything in the Slack.
Any in-person questions? If not, you can always post them in Python Learning later. Ping
Yep.
John on Slack.
And I will put the slides in there so you can like click on the links and that sort of thing.
Awesome.
So thanks,
Thank you,
folks.
John. Okay, you made it, everyone. All right, stop my video. Okay, so just a quick little wrap up here to sum up all of our experiences at the summer school so far. First, I just want to give a few thanks to Isa, of course, for hosting us here in Madrid. Yeah, and ISA Science Data Center for supporting the venue of 2 speakers, local transportation, and buffet dinner. And then, of course, NASA for funding myself and Sean on the PyHC leadership team, and for travel, lodging, and food for several of our in-person presenters here today. Our wonderful Arnaud Masson here in the back for organizing all things on the ISA side. He was a one-man team and doing a lot for us in the background, so thank you. Justina, who's here at ISA for all her administrative assistance. Inez for helping sort out details for the canteen so we could eat. Ellie and Alvaro up there in the back for setting up and handling audiovisual. That went awesome. All of our presenters for all the effort they put into putting together these presentations and then presenting them. Those of us on the org committee, I guess self-clap for putting this together. And of course, all of you and everyone online for making the trip out here, taking time to attend, for your questions, and for participating in our first rendition of the PyHC Summer Schools. Thank you. I'm not going to go through this all again, but I'll be sending these slides out. So I wanted you to know that for saving Helio content information, that'll be here and you'll have that soon. Just make sure to do it by next Wednesday, end of day Eastern time in the States. Brian and Jeff plan to spin down Helio Cloud after that point to save money. You can also get it all the notebooks and content again from the Summer School GitHub repo link there. Some other notes, we would really love to get feedback from all the attendees here and online on this summer school. There is a link to a survey there. I'm having Ashley post that also in the Slack in general. So later you can find it there when you have Wi-Fi again. If you could fill that out by next Friday, end of day Mountain Time where I'm at in Boulder, Colorado, that'd be great. And then we're not going to be immediately closing down Slack, but we will eventually. I'll save all the Slack output from all the channels so you can still have all the questions that people ask and so forth, and post that on the summer school webpage when we do that. And then finally, if you want to rewatch anything from the summer school, just go to our YouTube. You will find all of the recorded presentations there. And I think this is my last slide. So if you want to, second to last, if you want to connect after the summer school, if you have any more questions regarding the presentations, project, so forth, Slack will definitely be up through the end of next week, and we'll have presenters be sure to monitor that. Not quite as frequently as they were when they were here in person, but once a day or so. So feel free to post questions there. After that, you'll need to contact the developers via email or their own discussion channels, and we'll be sure to share all of that contact info with you when that time comes. And if you want to connect further with PyHC after this summer school, we have a mailing list you can get on. We have chat rooms. We have a Twitter, tweet us, and you can find all of this on our contact page. So go there. And thank you again, and hope to see you in the future. You can go now. Thank you.